Hello, my friend. I'm glad you found your way back here tonight. Whatever kind of day just ended for you, whatever you are carrying into this evening, you can set it down for a while. Get comfortable, get settled in, and let us spend this next stretch of time together the way we always do. Picture for a moment the very first people who ever called the British Isles home. Go ahead, picture them clearly. What colour is their skin in your imagination? For most of us, without even meaning to, the image that shows up is pale, fair. The classic freckled face of the English countryside, and for more than 100 years that was not just a casual guess. That was the official scientific assumption. Then, inside a quiet laboratory in London, a research team drilled a hole no wider than a pencil tip into a 10,000-year-old skull, and everything the world thought it knew about the oldest complete skeleton in Britain turned out to be wrong. Now, before we walk through that story together, a small favour if tonight is the kind of company you enjoy. Tapping that like button helps this little corner of the internet more than you would guess, and following along means you will be here for the next quiet evening like this one. If you feel like it, tell me down in the comments where you're tucked in tonight and what time it is where you are. I see every single one, and I love picturing exactly where these stories land all around the world while you listen. And if a night ever comes when you want to support this a little further, there is a small option for that too, though only ever if it feels right to you, never, because you have to. For now, dim the lights if you're able to let your shoulders drop and get as comfortable as you possibly can. Tonight we're going somewhere 10,000 years old. Before this night is over, we're going to meet a vitamin that your own body is still quietly protecting all these years later. We will follow farmers who carried one invisible single-letter mutation across an entire continent without ever knowing they were carrying anything at all. We will meet older cousins of ours who turned pale long before we did, for reasons that had nothing to do with us. And we will look honestly without flinching at a shade of skin that history once twisted into a weapon, and that modern science has only recently and rather gently set straight. All of that is still ahead of us tonight. But first we have to travel to a narrow limestone gorge in the west of England, and meet a man who's been waiting patiently for 10,000 years to be properly understood. Somewhere in those limestone hills, in a stretch of land that would one day be called Somerset, a young man moved carefully along the gorge floor roughly 10,000 years ago. Mist would have clung low to the rock that morning the way it still does in that part of England today. The world around him would have felt both familiar and strange to modern eyes. Wolves still moved through that landscape then. So did lynx and wild boar and enormous herds of deer that had not yet learned to fear the particular sound of a bowstring being drawn. He carried tools shaped from flint and bone worn smooth by his own hands, the kind of ordinary objects that would one day sit under museum glass, labelled and lit and stared at by strangers who could not begin to imagine him. He was in his early 20s, and by the standards of his time he appears to have been thriving. His teeth, examined carefully thousands of years later, showed almost none of the disease and decay that plagued so many people who came after him. He had likely eaten well that week. Meat, probably freshwater fish from the streams nearby, almost certainly. Nearby, tucked into the mouth of a cave that cut deep into the rock, his small community had built something like a home. Torchlight against damp stone. Low voices. The smell of wood smoke pressed tight against the cold outside air. We do not know his name. Nobody who loved him survived long enough to tell us. But we now know with more confidence than almost anyone else from that entire era of human history exactly what he looked like. And when you stop to actually sit with that fact, it is almost hard to believe. His story resurfaces in the spring of 1903 when workmen dig in a drainage trench inside a place called Guff's Cave deep in Cheddar Gorge, uncovered a skeleton so complete, so remarkably preserved, by the cool, dry, unchanging conditions inside that cave, that it remains even now, more than a century later, the oldest, nearly whole human skeleton ever found in Britain. The work itself was ordinary and unglamorous shovels and picks against packed earth, meant only to fix a drainage problem for the growing stream of Victorian tourists who had begun visiting the gorge for its scenery. Nobody expected history to interrupt a plumbing job, but one shovel struck something that was clearly not stone, and the digging slowed, then stopped completely while word was sent for someone who might actually know what they were looking at. The workmen could not have known what they had stumbled into. They gave the skeleton a nickname, borrowed simply from the gorge that had quietly protected him for 10,000 years, Cheddar Man. For most of the 20th century, that was almost the entire story. A skeleton in a glass case, a slightly amusing name that visitors chuckled at on school trips. Over the decades, several careful, honest reconstructions of his face were built based on the best evidence available at the time, and every single one of them without exception gave him pale skin and light, unremarkable eyes. This was not laziness, and it was not carelessness. It came from a quiet, almost invisible assumption that had followed European prehistory for more than a century, the assumption that ancient Britain must have looked more or less like the Britain we already knew. Pale skin felt obvious. It felt like the default setting for anyone who had ever called this cold, grey, rain-soaked corner of the world home. It is a small, useful reminder about how evidence actually works. Scientists were not being careless when they pictured him wrong for so many decades. They simply had no direct way before certain genetic techniques matured to test an assumption that felt too obvious to even question, and that in its own quiet way might be the most human part of this entire story. We tend to fill in the blanks of the past using the shape of right now, without ever fully realizing we are doing it until better evidence finally arrives and forces a correction. Have you ever assumed something about your own family's past, something you simply took for granted only to discover much later that you had it completely backward? Hold on to that feeling for a moment, because that is exactly what happened to an entire nation all at once in 2018. Inside a laboratory at the Natural History Museum in London, a small team that included researchers Selena Brace and Ian Barnes carefully drilled into the base of Cheddar Man's skull into a small, unusually dense bone near the inner ear, a bone that tends to protect genetic material far better than almost anywhere else in the human body. From that fragile bone powder, working alongside geneticists Mark Thomas and Johan Diekman at University College London, the team extracted and pieced together his entire genetic code fragment by fragment, letter by letter. What came back overturned more than 100 years of quiet assumption in a single afternoon. Cheddar Man had dark curly hair, he had strikingly blue eyes, and his skin, according to the genetic markers scientists now use to predict pigmentation, was dark. Not tan, not olive. The research team described it plainly as dark to black, with somewhere around 76% confidence in that specific shade based on the same markers used to study skin color in people alive today. It helps to understand just briefly how a team can even make a claim like that from a handful of ancient bone fragments. Skin tone is not decided by one single gene acting alone. It is shaped by a small handful of genetic switches, each one nudging melanin production up or down, and each one leaving a specific readable signature in a person's genetic code. Scientists build their predictions by comparing those exact signatures against enormous modern reference libraries, real people today, with known measured skin tones whose genetic patterns have already been mapped in careful detail. When Cheddar Man's ancient signature was compared against that library, it did not land anywhere near the pale end of the scale. It landed firmly, unmistakably on the dark end instead. Sit with that combination for a second. Blue eyes, black skin, buried in the quiet English countryside 10,000 years before anyone ever used the word England. How many of those earlier reconstructions, standing patiently in museum halls for decades, had gotten it exactly backward? How many school books, how many casual assumptions passed down at dinner tables about who the first Britons must have looked like needed to be gently, honestly rewritten overnight. And here is the detail that turns this from one strange isolated curiosity into something much bigger. Cheddar Man was not an anomaly. When his genetic profile was compared against other skeletons from roughly the same era, unearthed hundreds of miles away in what is now Spain, Hungary and Luxembourg, the pattern held firm. Dark skin, light eyes in several cases. An entire population of hunter-gatherers scattered across a huge stretch of Europe, all descended from people who had migrated up from warmer regions after the grip of the last ice age finally loosened roughly 12,000 years earlier. And every one of them, it seems, had simply not yet developed the pale skin we now think of as quintessentially unmistakably European. Scientists even have a name for this scattered group now. Western hunter-gatherers, a single sprawling population, connected less by geography than by ancestry, stretching from the Iberian coastline all the way up into the British Isles, all sharing the same dark-skinned, often blue-eyed appearance generation after generation, long after modern nations and modern assumptions about who belonged where existed at all. There is one more small detail worth pausing on here, mostly because it still makes me smile a little. Despite his name and despite the cheese that would one day make this exact gorge, famous Cheddar Man could not have digested a single glass of milk as an adult. The genetic tolerance that lets so many people in this region enjoy dairy comfortably had not evolved yet either. That particular trait would not arrive for thousands more years, carried in by an entirely different wave of newcomers in an entirely different chapter of this story. Even the cheese, in a strange sort of way, arrived after he did. Bringing his face back required more than a laboratory. Two Dutch model makers, brothers named Alphonse and Adrie Kennis, spent nearly 3 months turning raw genetic data into something the rest of us could actually look in the eye. Using 3-dimensional scans of the original skull as their foundation, they built up layers of muscle and tissue, almost the way a real face grows, working from bone outward rather than skin inward, then sculpted his features by hand layer by careful layer. They placed individual strands of dark curly hair one at a time, across a scalp that took days on its own to finish. And last of all came the detail that mattered most, a pale, unmistakable blue worked carefully into each eye. When researchers who had studied these particular bones for years finally stood in front of the finished bust, more than one of them described the moment as strangely emotional, even though the genetic data had already told them weeks earlier exactly what they were about to see. There is, it turns out, a real difference between knowing a fact on a printed page and standing quietly face to face with it. So why did pale skin take so long to arrive in a place this grey, this sun-starved, this seemingly perfect for it? Some researchers argue this is mostly a matter of population history, that the specific mutations for lighter skin simply had not reached this particular group of hunter-gatherers, yet even though the environment around them was already quietly favouring it waiting. Others point to something slower and messier, the idea that evolution rarely moves at the speed our imagination wants it to, and that 10,000 years, which feels impossibly long to us sitting here tonight, may simply not have been long enough. Perhaps it was one explanation. Perhaps it was both tangled together in ways researchers have not fully separated yet. Or perhaps, and this might be the most honest answer available, we're still only reading the opening page of a story that took hundreds of generations to write, and a few of its details may simply stay just out of reach. No matter how carefully we look, what we can say with real confidence is this: whatever finally did tip the balance toward paler skin in Northern Europe, it clearly was not simply arriving in a cold, cloudy place. Cheddar Man and his community had already been living under those same grey skies for thousands of years by the time he died, and the shift still had not happened. Something else had to occur first. Something we will spend the rest of this journey slowly, carefully uncovering. Here is what has stayed with me long after first learning about Cheddar Man. Somewhere between 8 and 10% of white British ancestry today can be traced back, at least in part, to people just like him, meaning his genetic fingerprint has quietly outlived him by 10,000 years, folded into hundreds of thousands of people who have never once thought to ask where it came from. Which means that somewhere out there right now, in a country famous the world over for pale, easily sunburned skin, there are people quietly going about their evening whose 10,000-year-old ancestor looked nothing at all like their own family assumed. History, it turns out, has a quiet sense of humour. And skin colour, that thing we so often treat as fixed, as ancient, as somehow written permanently into a place, and its people, is actually one of the most recent, most restless parts of the entire human story, which raises a much bigger question than one man in one cave in one corner of England. If pale skin was not always here, if it had not even reached Britain by 10,000 years ago, then where did it actually come from? To answer that, we have to leave this gorge behind completely and travel back much further than any single skeleton can carry us, all the way to the very beginning of human skin itself, to a time when every person alive on this planet, without a single exception, shed exactly the same shade. To find that beginning, we have to go back roughly 2 million years long, before Britain existed, long before Europe existed, long before most of the land masses we now name and argue over had ever been walked by anyone even remotely like us. Somewhere on the open grassland of East Africa, under a sun with real weight to it, a figure moved at a steady, relentless pace across the plain. Not sprinting. Nothing about early human survival depended on speed in short bursts. This figure moved the way a person moves when they intend to keep moving for hours, following the tracks of a wounded antelope that had slipped away from the group at dawn, trusting that raw endurance would eventually do what a spear alone could not. The ground beneath bare feet was cracked and pale with heat. Somewhere behind the rest of the hunting party had fallen back, unwilling or unable to keep the same relentless pace, willing to let one or two chase the animal to exhaustion while the group closed in later. The air shimmered off the dry earth. Sweat ran freely down bare skin, evaporating almost as fast as it appeared, carrying heat away from the body with every mile. Somewhere ahead, the antelope, built for short, explosive speed rather than hours of sustained heat, was slowly losing the only advantage it had. Its lungs would give out long before its legs did. That, in the end, was the entire strategy. Simply never stop. Here is the strange part, the part almost nobody guesses correctly on the first try. That bare skin, glistening under the equatorial sun, was very likely not dark yet. It may well have been pale. Think about our closest living relatives for a moment. A chimpanzee's skin, hidden underneath its thick coat of hair, is often startlingly light, sometimes almost pink. The hair carries the colour. The skin underneath, protected from direct sunlight, its entire life has never needed to defend itself against the sun at all. Our own ancestors for millions of years likely followed the exact same pattern. Fur did the work. Skin simply came along for the ride. So what changed? Somewhere between roughly 1 and 2 million years ago, our ancestors began losing that fur and gaining something. Almost nothing else on the savannah had in the same abundance. Millions of small, highly efficient sweat glands spread across bare skin, capable of cooling the body through evaporation, rather than panting the way most other mammals are forced to. A human being today can carry between 2 and 4 million of these glands. It is, by the standards of the animal kingdom, an almost absurd cooling system, and it may be the very reason a slow, weak, weaponless ape managed to out-hunt animals that could outrun it easily over any short distance. We could not catch the antelope in a sprint. We could outsuffer 1 hour after hour under conditions that would eventually stop almost anything else in its tracks. But losing that fur came with a serious immediate cost. Bare skin, once it lost the shade and protection that hair had quietly provided for millions of years, was now taking the full force of equatorial sunlight directly every single day for an entire lifetime. And that left evolution with a very narrow window to solve a very urgent problem. How do you actually put a date on something like this? There are no photographs from 2 million years ago. No skin fragments survive that long in African soil. For decades, this question sat firmly in the category of things scientists suspected, but could never quite prove. Then in the early 2000s, a geneticist named Alan Rogers working at the University of Utah came across an article about a gene called MC1R, the gene most directly responsible for switching human pigment production between two very different modes. One version of that switch produces eumelanin, a brown to black pigment that actively shields skin cells from ultraviolet damage. The other produces pheomelanin, a red to yellow pigment that offers barely any protection at all. Rogers noticed something curious buried inside earlier research on this gene. Among African populations, the MC1R gene showed almost no variation whatsoever. Not none, but remarkably suspiciously little, especially compared to how much this same gene varies among people outside Africa. To a population geneticist, that kind of unusual uniformity is not boring. It is a clue, the genetic equivalent of finding a single unbroken signature written across millions of people who have never met each other spread across an entire continent. When a version of a gene sweeps through an entire population because it offers such a strong survival advantage that almost nobody without it survives to pass on their own genes, it leaves behind a very specific fingerprint, a sudden narrowing of genetic diversity around that one spot in the genome. Working with two colleagues, David Iltis and Stephen Wooding Rogers, built a mathematical model around this fingerprint counting tiny invisible mutations that had accumulated since that narrowing occurred, using them almost like tree rings to estimate how long ago the sweep must have happened. It was slow, careful, unglamorous work, the kind that rarely makes headlines on its own, built from spreadsheets and statistical models rather than fossils or dramatic excavation. Their answer arrived with a number attached. Roughly 1.2 million years ago, and tucked inside that same calculation was a second, almost eerie detail. At the moment this gene swept through our ancestors, the entire breeding population involved may have numbered somewhere around 14,000 individuals. Sit with that for a second. 14,000 people. That is smaller than the crowd at a mid-sized college football stadium on a Saturday afternoon. Every single person alive today, every stranger you have ever passed on the street descends from a group of ancestors that could have comfortably fit inside a single sports arena. Why did the entire species share the same genetic solution so quickly, so completely? Because the alternative was brutal. Anyone born without adequate melanin protection, under that particular sun on that particular open landscape, was significantly more likely to suffer skin damage severe enough to affect survival and reproduction, generation after generation, without mercy or exception. Dark protective pigmentation was not a preference. It was closer to a requirement, the kind of requirement evolution enforces not through kindness, but through sheer repeated attrition. For a long time, the leading explanation for why stopped there. Protection from the sun, full stop, usually framed specifically around preventing skin cancer. It is a tidy explanation, and it even sounds correct. It fits neatly into a single sentence, which may be part of why it spread so easily through textbooks and documentaries for so many years. There's just one problem with it, and it is worth pausing on because it is exactly the kind of honest correction that good science is supposed to make, even when the original explanation feels satisfying. Skin cancers overwhelmingly strike later in life, often well past the years when a person is actively raising children. Evolution, blunt and indifferent as it is, has very little reason to select strongly against a danger that mostly arrives after someone has already passed on their genes. A biologist noticing this gap in the logic decades ago realized that skin cancer alone could not fully explain why this pressure was so intense, so fast, so nearly universal. Something else had to be happening beneath the surface, something quieter, something tied more directly to survival and reproduction during a person's most fertile years, rather than to old age at all. We are going to leave that particular thread hanging for now on purpose, because it deserves its own careful unravelling shortly. For the moment, what matters is this. By roughly 1 million years ago, give or take, our ancestors across Africa had become a dark-skinned, nearly hairless species walking upright beneath one of the harshest suns on the planet, having traded a warm coat for a built-in air conditioning system and a pale hide for a permanent shield. Which raises an obvious question. If every human being alive on Earth today truly descends from that same dark-skinned African population, how did any of us end up pale at all? For most of the 20th century, that question had no rigorous answer, only guesses. It took a married pair of researchers and roughly 10 years of quiet, unglamorous data collection to finally hand the world something like a real map. In the early 1990s, a biological anthropologist named Nina Jablonski, freshly relocated with her husband and research partner George Chaplin from Hong Kong to a new post in Perth, Australia, was asked to give a lecture. Jablonski had spent most of her career until that point studying old world monkeys, not human skin at all. But preparing for that single talk pulled her into a gap in the scientific literature that nobody had properly filled, and she never fully climbed back out of it. Over the following decade, she and Chaplin gathered two very different kinds of evidence and laid them directly on top of each other. On one side, decades of anthropological records documenting the actual skin tones of indigenous populations across the globe measured carefully region by region, much of it collected by earlier researchers using a simple handheld device called a reflectometer, pressed gently against a person's skin to measure exactly how much light bounced back. On the other side, freshly available satellite data, originally gathered for entirely different purposes, mapping the exact intensity of ultraviolet radiation, striking every square mile of the Earth's surface season by season. Piecing the two together meant years of unglamorous, painstaking cross-referencing, long before either of them knew whether the pattern would even hold. When they finally overlaid the two maps, the match was almost startling in its precision. Skin color wherever populations had lived largely undisturbed by recent migration for thousands of years, tracked the sun's intensity astonishingly closely. The darkest skin tones on the planet appeared almost exactly where the ultraviolet radiation was strongest. The palest tones clustered almost exactly where it was weakest. Not roughly, not approximately. A correlation strong enough to make the pattern feel less like a loose tendency, and more like a rule written directly into human biology, one that had simply been waiting patiently for somebody to finally lay the right two maps side by side. Here is a question worth sitting with for a moment before we move any further. If you traced your own family back far enough right past every nation, every war, every migration your ancestors ever made, do you know which patch of sunlight they were at some point quietly adapting to survive under? What Jablonski and Chaplin's map made undeniable was something far bigger than one skeleton in one English cave. Skin color was never a fixed marker of deep ancestry frozen in place since the dawn of humanity. It was closer to a dial adjusted again and again independently in different populations in different corners of the world, in direct response to how much sun a given landscape actually received. Populations that moved over enough generations saw their skin color shift right along with them. Populations that stayed in one intensely sunny place, generation after generation, stayed dark sometimes, for over 1 million years, without ever needing to change at all. It is worth saying plainly because it rarely gets said plainly enough. If you have ever taken one of those popular genetic ancestry tests, the kind that mails you a small tube and a colourful map, a few weeks later you may have noticed that skin colour itself is almost never part of the actual genetic breakdown. There is a reason for that beyond marketing. The genes tied most closely to your deep ancestral lineage, the ones tracing back tens of thousands of years, and the genes tied to your visible skin tone are simply not the same genes, and they do not move together in any dependable way. Two people can share a recent common ancestor and end up with very different skin tones. Two people with almost no shared recent ancestry at all can end up with strikingly similar ones, purely because their ancestors, however distantly related, happen to settle under a similar sun. If you're starting to feel your eyelids grow heavy right about now, that is exactly where I want you. Let yourself sink further into the pillow. And if you feel like sharing, tell me down in the comments quietly what time it is exactly where you are tucked in tonight listening to all of this in the dark. There is something almost humbling in this particular fact once it settles in properly. The very trait that human beings have spent centuries treating as a permanent defining marker of deep difference between groups of people is, biologically speaking, one of the most recent, most flexible, most quietly negotiable features we have. It changed before more than once in more than one direction. Under the right pressure across enough generations, it can change again. It has never been the ancient, unmovable line so much of human history has mistakenly treated it as. A handful of genetic switches reacting to nothing more complicated than sunlight did all of that work. Not deep ancestry, not separate origins, just skin responding the same way it always has to the same sun it has always known. Some researchers still debate the exact mechanics driving that first shift away from Africa, whether ultraviolet exposure alone fully explains the pattern, or whether something else, something happening quietly beneath the surface of the skin itself, deserves just as much credit. Others argue the picture is almost certainly layered several pressures working together, rather than any single explanation doing all of the work alone, each one reinforcing the others across enormous stretches of time. And a few of the more careful voices in this field will simply honestly admit that we may never fully separate every thread of a story this old one, that unfolded across 1,000,000 years largely without leaving behind a single written word, a single named witness, or a single surviving photograph. But one thread, the one we deliberately set aside a few minutes ago, is far too important to leave hanging much longer. Because hidden inside that early explanation, the one that could not fully account for why dark skin spread so fast, so completely, across an entire ancient population, is a substance most of us have heard of, but almost nobody associates with skin color at all. A vitamin, one your own body is still quietly and visibly protecting inside its bloodstream every single day, whether you've ever thought about it or not. That is exactly where we are headed next. In the summer of 1978, two American medical researchers, Richard Brander and John Eaton, ran a quiet experiment that had nothing to do with evolution at all. They were not paleoanthropologists. They were not digging through fossils or arguing about ancient migration routes. They were physicians working in a clinical laboratory, curious about a much smaller, much stranger question. What actually happens to the nutrients inside human blood when that blood is exposed directly to strong sunlight? The nutrient they chose to focus on has a name most of us already know, though almost nobody connects it to skin color at all. Folate. You may recognize it better by its more common name, folic acid, the one printed on the side of a prenatal vitamin bottle, or listed quietly among the ingredients on a cereal box you have probably never once stopped to actually glance at. Most people who take it every morning have no idea it may be the real reason an entire branch of the human family tree turned the color it did. It is worth picturing the scene for a moment because it is a far quieter kind of discovery than a dig site or a cave. No dust, no shovels. Glass vials of ordinary human blood plasma lined up under a lamp built to mimic the intensity of real sunlight, while two men in white coats simply waited and watched and measured. Nothing about the setup looked like it belonged in the story of why human beings around the world are different colors. And yet somehow that's exactly the story it was quietly about to tell. They exposed that plasma to simulated sunlight in the laboratory, the kind of intensity a person might experience on a clear afternoon near the equator. Then they measured what remained. Within a single hour, somewhere between 30 and 50% of the folate in that plasma had simply broken down, destroyed by the light itself. not blocked, not slowed, chemically dismantled as if sunlight were quietly picking a very specific lock inside the bloodstream. Then came the detail that made the discovery impossible to dismiss as a laboratory curiosity. Brander and Eaton looked at real patients, pale-skinned individuals undergoing ultraviolet light treatment for various skin conditions, a common dermatological therapy at the time. Those patients exposed to concentrated light for medical reasons rather than a day at the beach showed abnormally low folate levels in their actual bloodstream. Whatever had happened inside that laboratory dish was also happening quietly inside living human bodies. Here is a question worth sitting with for a second. Why would losing a vitamin matter enough to reshape the colour of human skin? Brander and Eaton were direct about the stakes in their original paper, and they did not soften the language. Folate deficiency, they noted, was already known to cause severe anemia, difficult and often fatal pregnancies, outright infertility, and elevated maternal mortality. The kind of consequences that left unaddressed across a population for long enough would have carved a very real, very measurable dent into how many children survived to adulthood and how many mothers survived to raise them. Folate is not a minor player tucked away in the background of human biology. It is one of the essential building blocks your body uses to synthesize and repair genetic material. The literal instructions every single cell relies on to divide correctly. Every time a cell splits into two somewhere in your body right now while you listen to this, folate is quietly involved in making sure that division happens without catastrophic errors. Skin cells replacing themselves, blood cells being manufactured deep inside bone marrow, hair follicles, gut lining the entire quiet machinery of a body, constantly rebuilding itself one cell at a time day after day without you ever noticing the labour involved. And most critically of all, for a species trying to reproduce and survive, the extraordinarily rapid, extraordinarily delicate cell division that builds an entire human embryo from a single fertilized cell into a living, breathing infant in the span of only a few short months. There is a specific window, astonishingly early, astonishingly narrow when this matters most, within the first month after conception often, before a woman has any idea she's even pregnant. A structure called the neural tube is forming the earlier scaffolding of what will eventually become a baby's brain and spinal cord. If folate is scarce during that narrow window, that structure can fail to seal correctly. The result is what doctors call a neural tube defect conditions like spina bifida, where the spine does not fully seal, or the far more severe anencephaly, where the brain itself fails to develop completely. These are not rare curiosities from a medical textbook. They are one of the more common, most devastating classes of birth complications in human history, and they trace back to a single vitamin at a single moment weeks before most expectant mothers would ever think to worry about it. Sit with that timing for a moment. Weeks before most women even know, which means evolutionarily speaking, any factor capable of quietly depleting folate throughout a population generation after generation without anyone ever understanding why would apply constant brutal pressure on reproduction itself. Not occasional pressure, not once in a lifetime pressure, relentless repeating pressure every single pregnancy, every single generation. For as long as that population lived somewhere, the sun struck hard and often. And pregnancy was never the entire story. Brander and Eaton's original paper noted something else, almost in passing, that deserves far more attention than it usually gets. Folate deficiency was also linked to outright infertility and separately to impaired sperm production in men. This detail tends to get lost because the more emotionally resonant version of this story, the one about a developing embryo, understandably pulls most of the attention. But the underlying biology does not care about which version makes for a better headline. Producing healthy sperm, just like producing a healthy embryo, requires rapid, accurate cell division over and over for an entire adult lifetime, not only during a 9-month window. This was never only a story about mothers and unborn children, though That is the version most often told. It was a story about an entire population's capacity to reproduce at all, men and women both, quietly undermined by nothing more dramatic than spending too many unprotected hours under a merciless sun. For more than 20 years after Brander and Eaton first published their findings, this particular idea sat mostly quiet-sighted occasionally, but never fully woven into the bigger picture of human evolution. It took another set of researchers willing to reach across completely different fields, dermatology on one side, paleoanthropology on the other, to finally connect a finding about hospital patients under a sun lamp to a story that began on the plains of East Africa. Some of the most important discoveries in science do not arrive as sudden thunderclaps. They arrive quietly, get set down on a shelf, and wait patiently for the right person to come along and ask the bigger question nobody had thought to ask yet. 22 years after that first quiet laboratory, finding the researchers you already met, Nina Jablonski and George Chaplin, picked up this exact thread and pulled it much further. Their argument, published alongside the global ultraviolet map we already walked through, was that folate protection, not simply sunburn, not simply skin cancer risk decades down the line, was likely the dominant force behind the sheer speed and completeness of early dark pigmentation. A population living directly under equatorial sunlight without adequate melanin protection was not facing a slow generational disadvantage. It was facing repeated compounding damage to its own ability to successfully reproduce pregnancy after pregnancy in the very years when reproduction mattered most. In a sense, they took a finding from a dermatology clinic meant to explain something happening to patients in the 1970s and reached backward with it over roughly 1 million years to help explain why an entire species turned the shade it did in the first place. That reframes something we touched on earlier, and it is worth naming plainly. Evolution does not particularly care whether an adult eventually develops a health problem at 60 or 70 years old, long after their children are already grown. But it cares enormously about anything that interferes with a successful pregnancy at 20 or 25 or 30. Folate photolysis was not a distant abstract risk. It struck exactly where natural selection is most unforgiving at the moment of conception itself, again and again without pause for hundreds of thousands of years. If you ask most people off the top of their head why dark skin evolved in the first place, you will almost always get some version of the same tidy answer. To stop sunburn. To prevent skin cancer. It is not a wrong instinct exactly, and both of those things are real secondary benefits of melanin. But it is an incomplete answer, and arguably not even the most important one. Sunburn is uncomfortable. Skin cancer, as we already discussed, mostly arrives decades too late to matter much to natural selection. A quietly failing pregnancy, weeks after conception, before anyone even realizes it happened, is a different category of consequence entirely repeating itself in every single generation with no exceptions. The popular explanation focuses on the skin protecting itself. The deeper explanation is that skin was protecting something running through it, invisible, easy to overlook, and far more urgent. Here is where the story quietly reaches all the way into your own bathroom cabinet, whether you've ever noticed it or not. Since January of 1998 in the United States, nearly every enriched bread, cereal, pasta, and flour product on grocery store shelves has been legally required to contain added folic acid, specifically because of this exact vulnerability. It was not a marketing decision. It was a direct public health response to devastatingly consistent data linking folate deficiency to neural tube defects. Before that requirement took effect, researchers estimate that roughly 4,000 babies were born in the United States each year with a neural tube defect, and nearly 1,200 of those infants did not survive it. In the years immediately following fortification, that yearly number dropped to somewhere closer to 3,000. Spina bifida cases alone fell by roughly 30%. Anencephaly declined as well, though somewhat less dramatically, An ancient evolutionary pressure, one that helped decide something as fundamental as human skin color hundreds of thousands of years ago, is still right now being actively managed by regulation on the side of a cereal box. Whether the person pouring that cereal into a bowl has ever thought about it for even a second. Have you ever picked up a prenatal vitamin or watched someone in your life take one and wondered exactly why folic acid gets top billing on the label ahead of nearly everything else inside that little pill? Now you know. It is not a modern invention. It is one of the oldest, most consistent pressures human biology has ever faced, simply given a new, more convenient delivery method. There is a small, quietly ironic postscript worth mentioning here too. Modern researchers studying this exact photolysis effect have noted that people with very fair skin today, especially those who spend long stretches of time outdoors under strong sun without much protection, can still measurably deplete their own folate levels through their skin in a much smaller echo of exactly what Brander and Eaton first documented in that laboratory nearly 50 years ago. The ancient pressure never actually vanished. It simply stopped being a matter of life or death for most of us, thanks to fortified bread and multivitamins, rather than skin alone having to carry the entire burden. Not every researcher in this field agrees on exactly how much weight folate protection deserves compared to the older skin cancer explanation we set aside a little earlier, or compared to a handful of other quieter possibilities still being investigated. Things like general resistance to skin infection, or protection against the simple physical breakdown of structural proteins in skin, exposed to decades of harsh sunlight. Some scientists argue the folate evidence, while compelling, remains difficult to test directly against events that happened the better part of 1 million years ago, since nobody can measure the blood folate levels of a population that vanished long before writing existed. Others counter that the reproductive stakes involved are simply too severe, too immediate, and too consistently supported by modern laboratory data to have played anything less than a leading role. And a few of the most careful voices in this field will tell you honestly that it was very likely never just one single pressure acting alone, but several layered quietly on top of each other, each one reinforcing the same outcome from a slightly different angle, in a way we may never be able to fully separate thread by individual thread. If you're the kind of person who finds real comfort in tidy single-cause explanations, I understand the appeal, and I will admit this particular chapter of the story refuses to offer one. What it offers instead is something a little more honest. A body quietly defending its own capacity to create the next generation, doing so through nothing more sophisticated than pigment in skin, long before anyone involved had the faintest idea why it mattered, or that it was even happening at all. There is something quietly moving about that if you let yourself sit with it. Long before medicine, long before language, long before anyone could name a single gene or vitamin, the human body was already keeping careful wordless score generation after generation, protecting exactly what it needed to protect. If your eyes are starting to feel heavy right about now, let them. There is nowhere else you need to be, if you feel like it. Let me know down in the comments where exactly you're curled up tonight listening to this in the dark folate, quietly doing its work inside you the entire time the way it has for every person who has ever lived. But protecting folate was never going to be the end of this story, and here is exactly where it gets more complicated. Because the same skin that so effectively shields folate from destruction also blocks something else your body needs almost as urgently, a second nutrient working through the exact same patch of skin, demanding almost the opposite conditions to be made at all. One vitamin needed shade, another needed sun, and no single shade of human skin could ever fully satisfy both at once. That collision, quiet, biological, and entirely unavoidable, is exactly where we are headed next. Berlin in the winter of 1918 into 1919 was a city running on almost nothing. The war had just ended, coal was scarce, food was scarcer, and an entire generation of children in the city had grown pale, weak and strangely misshapen, their legs curving outward under their own small body weight, their chests sometimes pushing forward into odd beaded ridges along the ribs. A pediatrician named Kurt Huldschinski, freshly back from serving as a field medic through the war, took a post at a home for frail children on the outskirts of the city, working alongside an orthopedist named Konrad Bisalski, a man already well known for his tireless efforts on behalf of disabled and chronically ill children in Germany. Huldschinski had a hunch unusual enough that most of his colleagues would have dismissed it outright, built loosely on decades of scattered, half-believed folklore suggesting that sunlight itself, not just fresh air, might carry some kind of healing property doctors had never properly measured. He selected 4 of his young patients for an experiment, including a 3-year-old whose full name history never preserved, remembered only as Arthur. Huldschinski placed them under mercury quartz lamps machines originally built for entirely different medical purposes that gave off an artificial version of ultraviolet light. Picture it for a moment. A cramped clinic room, cold despite the season 4 small children arranged beneath a strange humming apparatus that buzzed and glowed faintly violet, while nurses hovered nearby, half curious and half openly skeptical that any of this could possibly help. Nothing about this looked like medicine as anyone understood it at the time. There was no injection, no surgery, no new drug. Just 4 children sitting quietly under an odd humming light week after week, while a young pediatrician who had barely survived a war himself waited to see if his hunch would hold. Their bones began to change. By the time spring finally arrived and real sunlight returned to Berlin, Huldschinski moved his small group of patients out onto the terrace into direct sun, and the improvement continued exactly the same way it had under the lamps. When he published his results in a German medical journal in 1919, the reaction was somewhere between disbelief and quiet astonishment. He would later be nominated for a Nobel Prize for the work. And the number that made his discovery so urgent in the first place is almost hard to say out loud. At that moment in history, researchers estimate that nearly half of all children in Germany showed some degree of this same bone-softening condition. Not a rare disorder. A near majority experience of an entire generation's early childhood. The condition is called rickets, and it had a nickname long before Huldschinski ever picked up a mercury lamp. Physicians across continental Europe had taken to calling it the English disease, a name first recorded by a Polish doctor in the early 1800s, after noticing how devastatingly common it had become in the smoke-choked, sunlight-starved cities of industrializing Britain. Factories burned coal around the clock. The resulting smog hung low over entire neighborhoods for weeks, at a stretch thick enough to filter out much of the ultraviolet light that would otherwise have reached the streets below. Working families crowded into narrow, poorly lit housing, and children of laboring parents spent long hours indoors or in factory work themselves, rather than playing outside in whatever pale sunlight London or Manchester or Glasgow could offer. In some English districts during the worst years of the Industrial Revolution, more than half the local population showed signs of it. Even animals in the London Zoological Gardens developed it, which tells you something rather blunt about exactly how little usable sunlight was reaching the ground in those neighbourhoods at all. Here is the piece of biology sitting underneath all of it. The piece nobody in Huldschinski's era could yet fully explain, though they could clearly see it working. When ultraviolet light strikes bare human skin, it triggers a chemical reaction just beneath the surface, converting a cholesterol-like compound skin cells already contain into the raw material your body needs to make vitamin D. That vitamin in turn is what allows your intestines to actually absorb calcium from food, rather than simply letting it pass through unused. Without enough of it growing, bones do not harden properly. They stay soft, pliable, easily bent by the ordinary daily pressure of a child's own body weight. Legs curve outward, ribs distort, skulls can even grow strangely soft in infancy. And here is where this story does something I didn't expect the first time I properly understood it. Remember the trait we spent so long tracing in an earlier part of tonight's journey, the dark protective pigmentation that saved our earliest ancestors from a very different, very serious danger under the equatorial sun. That exact same pigment, the one that once quietly guarded pregnancies and prevented birth defects by shielding a vulnerable vitamin from being destroyed, becomes something else entirely once a population moves far enough from the equator. Melanin does not selectively block only the wavelengths of light that damage folate. It blocks a wide swath of ultraviolet light altogether, including the specific wavelength skin needs to manufacture vitamin D in the first place. The very shield that saved one generation could in a much dimmer, much colder climate quietly starve the next. There is no villain in this particular chapter of the story, no wrong turn, no mistake anyone made. There is only a single biological tool doing exactly what it was built to do in an environment it was never originally built for. Is that not a strange kind of irony? The same biological tool doing opposite jobs depending entirely on where on the planet a person happened to be standing. We are not talking about a minor inconvenience here either. Just like the story we uncovered, this one circles back eventually to childbirth itself. Severe rickets in early childhood could leave a permanent mark on the skeleton that would not fully reveal its consequences until decades later. In women, specifically, rickets could reshape the pelvis itself, as it grew, narrowing and flattening the very passage a baby would eventually need to travel through during labor. Right up through the early 20th century, a childhood case of rickets could mean a labor that simply could not proceed naturally. When that same woman became pregnant as an adult, an obstruction with no safe resolution before the arrival of modern surgery. Physicians of the era documented case after case, where the only recorded option in the absence of a surgical delivery was to induce labor artificially weeks before term in the desperate hope that a smaller, earlier infant might still manage to pass through a pelvis that had been quietly narrowing since childhood, without either mother or physician ever fully understanding why. Medical historians studying this period have identified rachitic pelvic deformity as one of the leading causes of maternal death across large stretches of industrial Europe, right alongside the very complications we discussed earlier, tied to a completely different vitamin. Sit with that for a moment. Two entirely separate nutrients operating through completely different biological pathways, and both of them independently converging on the exact same evolutionary pressure point. Childbirth. Not sunburn. Not a rash. Not cosmetic inconvenience. The literal ability of a population to bring the next generation safely into the world. It is worth noticing how rarely this version of the story gets told. Popular explanations of skin color evolution tend to reach for tidy single images: a farmer working under a hot sun, a fair-skinned tourist getting burned on vacation. The far less comfortable truth is that two of the most plausible explanations both circle back to the same place: a woman's body at the exact moment it is trying hardest to bring new life into the world, quietly succeeding or failing based on nothing more dramatic than how much unfiltered sunlight her ancestors and her own childhood happened to receive. Here is a question worth turning over quietly for a second if you allow yourself to. Somewhere in your own family history, going back far enough generations, you will never know the names of made it through exactly this kind of narrow, biological bottleneck. Whatever shade your skin happens to be tonight is in some small part a quiet echo of exactly how they managed it. Once you see both pressures side by side, folate collapsing under too much sun, vitamin D collapsing under too little, an obvious and rather elegant tension starts to come into focus. A population living directly on the equator faces overwhelming pressure toward dark skin because folate protection there matters enormously, and there is more than enough sunlight left over, even after melanin blocks a large portion of it, to still manufacture adequate vitamin D. But move that same population far enough away from the equator into the shorter days and weaker, more slanted sunlight of northern Europe, or northern Asia, and the entire calculation flips. There simply is not enough ultraviolet light reaching the ground anymore to punch through heavy pigmentation and still make sufficient vitamin D, especially not through the long grey months of winter. Something eventually had to give. It helps to picture the geometry involved because it really is mostly geometry. Near the equator, sunlight strikes the ground almost straight on concentrated, intense, abundant for something near 12 hours a day all year round. Move toward the poles, and that same sunlight arrives at a shallow glancing angle, spread thin across far more atmosphere before it ever reaches skin, and for a large portion of the year, in the depths of winter, the specific wavelength needed for vitamin D production barely reaches the ground at all, no matter how pale a person's skin might be. Even the lightest skin in the world cannot manufacture vitamin D from a sun that barely clears the horizon for a few short hours each day. This is in essence the quiet mechanical engine sitting underneath almost everything we have discussed so far tonight. Two opposing vitamins, two competing forms of protection, pulling human skin in opposite directions depending purely on latitude, on cloud cover, on how many hours of usable sunlight a given patch of the Earth actually receives across an entire year. It is also, in fact, the piece that finally completes the map we traced together earlier in this journey, the one built from years of satellite data and skin tone measurements collected across the globe. That map showed where light and dark skin actually ended up. What it could never show on its own was why the boundary sat exactly where it did rather than somewhere else entirely. Two competing vitamins pulling in opposite directions explain far more of that boundary than either pressure could ever explain alone. Not every researcher weighs these two pressures exactly the same way. Some argue that vitamin D scarcity was the more urgent, more immediate danger driving pigmentation change as populations moved north, since bone development affects every single child in a population, not only pregnancies at a specific vulnerable stage. Others maintain that folate protection near the equator was the stronger, more foundational force, and that lighter skin at higher latitudes emerged more gradually, more unevenly shaped by a whole tangle of additional factors, diet, clothing, shelter, and cultural habits that changed how much bare skin actually met the sky in the first place. A community that ate large amounts of fatty fish rich in vitamin D on its own might have faced far less pressure to lighten than a community relying mainly on grain. A culture that wrapped its children heavily against the cold for entirely unrelated reasons may have accidentally worsened the exact problem it never knew it was creating. And a few of the more careful voices studying this today will tell you plainly that we may be arguing over the exact proportions of a recipe whose full ingredient list we still do not fully possess even now with every modern tool available to us. What almost nobody in this field seriously disputes anymore is the shape of the trade-off itself. Skin color was never simply decoration, and never simply a matter of comfort under a hot sun. It was a running negotiation between two invisible life-or-death nutritional needs conducted silently across hundreds of thousands of years, with childbirth itself sitting quietly at the center of the whole arrangement the entire time. There is a small, almost tender postscript to Hulczynski's story worth adding here. His discovery did not stay confined to medical journals for long. Within a decade, public health campaigns across much of the industrialized world had begun actively fortifying milk with vitamin D, precisely to make sure children growing up far from the equator, or simply far from enough daylight, would never again need an experimental lamp to keep their bones from bending under their own weight. It became such a routine, unremarkable part of daily life that most people today pour a glass of fortified milk without a single thought for the desperate improvised science that made it necessary in the first place. An entire chapter of human suffering quietly solved and just as quietly forgotten. So the real mystery left standing is not why this tension existed. That part by now makes a strange kind of sense. The real mystery is how a population's skin could actually shift in response to it generation after generation without anyone alive at the time understanding vitamins or genes or ultraviolet light at all. If you feel your body starting to settle further into the mattress right about now, that is exactly the right moment for it. Let your breathing slow down along with mine. If you would like to share down in the comments where you're lying tonight and how far you happen to be roughly from the nearest coastline or the nearest patch of open sky. It is a strange thing to wonder about right before sleep, but after tonight you may never look at a sunny window quite the same way again. That answer was not sitting in a Berlin children's clinic or an English factory town. It was buried somewhere far stranger inside a single, almost invisible letter, hidden deep in human genetic code, waiting for a very different kind of scientist to finally go looking for it. A pathologist named Keith Cheng was not looking for it at all. That is worth saying plainly right at the start, because almost nothing about the way this discovery happened fits the tidy image most of us carry around of how science works. Cheng ran a laboratory at Penn State College of Medicine in the small town of Hershey, Pennsylvania, and for the better part of a decade his actual focus was cancer, not skin color, not evolution, not human history at all. His tool of choice was an unglamorous little aquarium fish called the zebrafish chosen because it breeds quickly, grows transparent as an embryo, and happens to share an enormous portion of its genetic code with us. Picture the lab itself for a moment. Rows of glass tanks humming under fluorescent light. Thousands of finger-length striped fish darting back and forth, while researchers in white coats leaned over microscopes, hunting for the subtle genetic glitches that might one day explain something about human tumours. Skin colour was nowhere on the agenda. Somewhere among his tanks of ordinary striped zebrafish sat a different, quieter strain, one that breeders and researchers had nicknamed golden. Instead of the sharp, dark stripes running down a normal zebrafish's body, these fish carried faint, pale, almost washed-out bands instead. For most labs, an oddly coloured fish would have been a footnote, mildly interesting at best. Cheng's team looked closer under a microscope at the actual pigment granules packed inside each fish's skin cells, tiny structures called melanosomes. In the golden fish, those melanosomes were fewer in number, smaller in size, and far less densely packed with pigment than in their normal, dark-striped relatives. Here is the detail that turned a minor aquarium curiosity into one of the more important discoveries in the entire story of human skin. Cheng's team already knew from earlier research into human pigmentation that this exact same pattern, fewer melanosomes, smaller melanosomes, less densely packed pigment, was precisely what separated the skin cells of people with European ancestry from the skin cells of people with West African ancestry. Cheng later admitted with a kind of quiet disbelief that seeing an identical pattern show up in a fish tank was not something anyone on his team had anticipated. A cancer lab staring at a slightly pale aquarium fish had accidentally stumbled onto a working model of one of the oldest unanswered questions in human biology. What happened next was slow, careful, unglamorous detective work, the opposite of a dramatic discovery montage. Cheng's team spent years narrowing down exactly which gene somewhere across the zebrafish's entire genome was responsible for the golden colouring. A painstaking process called positional cloning, essentially closing in on a single suspect by patiently eliminating everything else. Chromosome region by chromosome region, the genetic equivalent of searching an entire city block by block for one specific address with no street signs to guide you. They eventually isolated the culprit, a gene that would come to be called SLC24A5, which builds a protein sitting on the membrane of the melanosome itself, quietly managing the flow of sodium and calcium in and out of that tiny pigment-producing structure. Something like a tiny tireless gatekeeper standing at the door of the cell's own pigment factory. In the golden zebrafish, a mutation had cut that protein short by nearly half its normal length, and the gatekeeper simply could not do its job properly anymore. The result was a fish with paler stripes melanosomes that never quite filled up the way they were supposed to. The obvious next question was whether humans carried any version of this same genetic switch. Chung brought the question to a colleague across campus, a Penn State anthropologist named Mark Shriver, who had already spent years studying the genetics of human pigmentation. Shriver had access to something brand new at the time, a freshly released public catalogue of human genetic variation, built collaboratively by research institutions around the world, cataloguing small differences in genetic code across different populations for the very first time in one searchable place, the kind of resource that simply had not existed even a few years earlier. What had once required years of laborious individual sequencing could now, in theory, be searched in an afternoon provided you knew exactly what you were looking for. Searching through it for variations in the human version of Cheng's gene, Shriver found exactly what he was looking for. A single amino acid at a single specific position along the protein came in two versions. One version, far more common among people of West African ancestry, kept the original ancestral form of the protein fully intact. The other version, found at strikingly high frequency among people of European ancestry, carried one small substitution at that exact spot, one building block swapped for another, nothing more dramatic than that. Sit with that for a moment. Somewhere inside the 3 billion letters that make up the human genetic code, one single letter, at one single position in one single gene, was doing an outsized amount of work in deciding how light or dark a person's skin would be. To prove it was not coincidence, the research team measured actual skin pigmentation in over 300 people of mixed European and West African heritage, using a device that reads how much light reflects off skin, rather than relying on anyone's subjective description. The pattern that emerged was almost embarrassingly clean. People carrying 2 copies of the newer variant measured lightest. People carrying 2 copies of the older ancestral variant measured darkest. People carrying one of each landed neatly in between exactly the kind of dose-dependent relationship a geneticist dreams of finding and rarely actually does. There is something worth pausing on in exactly how that tiny sodium and calcium gatekeeper actually does its job, because the mechanism itself turns out to be almost elegant in its simplicity. Melanin, the pigment responsible for skin color, is built and stored inside melanosomes only once those internal compartments reach the correct chemical balance, an environment neither too acidic nor too neutral, finely tuned by the steady traffic of charged particles moving in and out. Disrupt that traffic even slightly, and the whole production line downstream slows to a crawl. It is less like a single switch, flipping from on to off, and closer to a thermostat set very slightly lower 1 degree at a time across an entire population over an unimaginable number of generations, until the accumulated difference became something you could see with your own eyes from across a room. When the full result was finally calculated, it landed somewhere that even the researchers themselves seemed almost reluctant to fully believe. This one gene, this one tiny letter swapped inside it, accounted for somewhere between roughly a quarter and just over a third of the entire measurable skin color difference between people of European and West African descent. Not a small contributing factor buried among dozens of others. A leading actor hiding in plain sight inside a fish tank in central Pennsylvania. Here is why that number should truly surprise you if you know anything at all about how most human traits actually work. Height intelligence. Most disease risk nearly every complex human characteristic scientists have ever studied closely tends to be shaped by hundreds, sometimes thousands of different genes, each one contributing only the tiniest sliver of the overall picture, the genetic equivalent of thousands of individually quiet voices in a crowd, none of them loud enough on their own to be picked out. Skin color itself is known to involve well over 100 different genes working in loose coordination. Finding a single gene responsible for nearly a third of such a visually striking difference is not the expected outcome. It is closer to an outlier, a strange exception to almost everything researchers thought they understood about how complicated human variation is supposed to be built. One voice in that enormous crowd somehow shouting loud enough to be heard clearly over all the others combined. Have you ever assumed that something as visually obvious as skin color must have an equally complicated, equally tangled explanation behind it? It is a completely reasonable assumption. It also happens to be only partly true. Some of the story really is complicated, spread thin across a great many genes working together, but a surprisingly large slice of it, at least for the specific difference between European and West African skin, comes down to one letter changed once a very long time ago. When Cheng and his colleagues finally published their findings in the journal Science in December of 2005, the reaction moved well beyond academic circles almost immediately. Newspapers ran headlines that tried with varying degrees of grace to compress an entire decade of accidental cancer research into something a general audience could digest over morning coffee, most of them leaning hard on the sheer novelty of it all. A fish tank in Pennsylvania, somehow explaining something about human skin that centuries of philosophy, politics, and pseudoscience had gotten wrong or left unanswered. Television crews wanted simple sound bites about a topic that, as we have already spent an entire journey establishing tonight, has never once been simple. Cheng himself, reflecting afterward on what his team had actually found, pointed out something quietly striking about the whole affair, that a single nucleotide, one letter out of 3 billion, carried an outsized amount of historical weight given everything human beings have done to one another over the centuries, partly on the basis of exactly this kind of surface-level difference. It is worth letting that sit for a moment rather than rushing past it. So much of human history, entire systems of law, entire wars, entire generations of cruelty and suspicion, organized itself around a difference that a fish tank in central Pennsylvania could ultimately trace back to one flipped letter, sitting quietly inside a gene most people will never learn the name of. There is a small, sobering footnote worth sitting with here too before we move any further. This particular genetic switch, so dominant across European populations, turns out to be almost entirely absent from East Asian populations, despite the fact that East Asian skin tones can sit in a truly similar range to many European skin tones. Whatever gave East Asia its own version of lighter skin, it was clearly not this same gene doing the same job the same way. That particular puzzle deserves its own careful unpacking later, because the honest answer turns out to be far stranger than most people expect. Not every question about this discovery has a settled answer even now, 2 decades later. Researchers still debate exactly how strong and how sudden the pressure favouring this particular variant must have been to spread as thoroughly as it did through European populations in what is, evolutionarily speaking, a fairly narrow window of time. Some argue the pattern in the genetic data points toward an unusually fast, unusually intense sweep, the genetic equivalent of a single winning idea spreading almost overnight. Others caution that apparent speed in ancient genetic data can be deceptive-shaped, as much by which ancient populations happen to survive and leave descendants as by the raw strength of the original selective pressure itself. And a few researchers more cautious still will remind you that a single striking gene, remarkable as it is, was never the entire story on its own, only the loudest voice in a much larger, quieter chorus of genetic changes working together across the genome, the other 100+ contributors quietly doing their own smaller share of the work in the background, largely unnoticed, mostly uncelebrated. If you feel your eyelids growing heavier with every paragraph, now good. That means this is working exactly the way it should. Let your shoulders drop a little further into whatever you're resting against. If you would like to tell me down in the comments what first drew you to a story like this one tonight out of everything else you could have been doing right now instead. If you are the sort of person who finds it comforting to imagine science as a place with tidy narrative arcs filled with heroes who set out looking for exactly what they eventually find, this particular chapter probably will not offer you that either. What it offers instead feels a little more true to how discovery actually tends to happen. A scientist chasing an entirely different question. A fish tank nobody expected to matter. A single letter waiting patiently inside 3 billion others for someone curious enough and lucky enough to finally notice it was even there. If you've ever taken one of those consumer genetic ancestry tests and scrolled past a section quietly labelled something like pigmentation traits, there is a real chance the exact gene we just spent the last several minutes with was sitting somewhere inside that report working away in the background completely unannounced. But finding the letter itself was never going to be the end of this story. A single mutation appearing once in one person thousands of generations ago does not automatically explain how it ended up carried by the overwhelming majority of an entire continent's population today. Somebody had to carry it somewhere. Somebody had to survive long enough and reproduce successfully enough for that one small genetic accident to eventually become the rule rather than the exception across an enormous stretch of the world. Researchers who later traced the ancestry of this exact mutation across thousands of modern genomes found something that still feels almost improbable to say out loud. Every single copy of it in every European carrier alive today appears to descend from one shared original chromosome, one person, one moment passed down an unbroken chain ever since. And the people responsible for carrying that inheritance across an entire continent were not sitting quietly in one place at all. They were walking generation after generation, carrying an entire way of life with them into a landscape that had never seen either of them before. They came from the hills and river valleys of a region we now call Anatolia, the peninsula, that makes up most of modern Turkey, and they were not explorers in any romantic sense of the word. They were farmers moving slowly, deliberately, generation by generation, carrying seed-grain-penned livestock and an entirely new way of living off the land that human beings in Europe had never encountered before. Picture the pace of it. Honestly, nothing like a march or an invasion closer to a family clearing one more field, a season's walk beyond their parents' village, their children doing the same, a generation later an unhurried tide advancing a handful of miles at a time, decade after decade, century after century. Roughly 10,000 years ago, the earliest waves of this migration began pushing north and west, first into the Aegean, then further still into the Balkans and eventually across the whole of the European landmass, over the course of many centuries rather than any single dramatic journey. They had no idea what else they were carrying with them. Buried quietly inside their own bodies, already common throughout their home population, before a single one of them ever packed up a wagon or herded a flock westward, was the exact genetic variant we spent an entire chapter of this journey tracking down the single altered letter inside a gene called SLC-Q4A5. It was not something they chose or understood or even could have perceived. It simply came along embedded in their skin, the same way it had been embedded in the skin of their parents and grandparents, stretching back to that one original chromosome we uncovered earlier. Here is where an easy assumption tends to sneak in, and it is worth naming directly before we go any further. You might reasonably expect that once these farmers arrived and once that gene entered the wider European population, through generations of intermarriage with the hunter-gatherers already living there, light skin would have spread across the continent fairly quickly, a done deal within a handful of centuries. That is almost exactly what scientists themselves assumed for a very long time, and it is not an unreasonable assumption on its face. A useful mutation arriving in large numbers spreading through a growing farming population that would eventually outnumber the older hunter-gatherer groups many times over sounds like exactly the kind of scenario evolution should move through swiftly. It is also, according to the most detailed reconstruction of ancient European pigmentation, we currently have simply not what happened. In 2025, a research team based at the University of Ferrara in Italy led by geneticist Guido Barbugiani and evolutionary biologist Silvia Girotto, alongside colleague Silvia Peretti, published a study that quietly upended decades of assumption. Working with fragments of genetic material from 348 ancient individuals spread across 45,000 years of European prehistory, the team developed a careful statistical method for estimating skin eye and hair color, even from badly degraded ancient samples, the kind of incomplete genetic wreckage that usually frustrates this sort of analysis entirely. It is worth appreciating what a genuine technical hurdle that is. Ancient bone does not hand over clean, complete genetic information the way a modern blood sample does. It offers fragments, gaps, damaged sections, sometimes barely enough usable material to work with at all. Building a method reliable enough to trust with such incomplete evidence took years of careful statistical groundwork before a single ancient skin tone could be confidently estimated. They tested their approach against two exceptionally well-preserved genomes, one from a man who lived in Siberia 45,000 years ago, another from a 9,000-year-old individual recovered in Sweden, and found that their method held up reliably even under difficult conditions. What they found once they applied that method across the full sweep of European prehistory was not a tidy, steadily rising curve of ever lighter skin marching neatly toward today. It was something far messier, far slower, and considerably more human. Across the entire span of time, the study covered roughly 63% of ancient individuals sampled showed dark skin. Only about 8% showed truly light skin. Everyone else fell somewhere in an intermediate range. And here is the detail that should honestly stop you for a moment. Even well into the Copper and Iron Ages period, stretching from roughly 5,000 to 3,000 years ago, thousands of years after those Anatolian farmers had already crossed the continent, fully half of the people sampled from that era still carried dark or intermediate skin, not the pale northern European colouring most of us instinctively imagine when picturing ancient Europe at all. Does that not completely upend the picture in your head? An entire continent thousands of years after agriculture had already taken root, still overwhelmingly populated by people whose skin looked nothing like the version of European ancestry. Most modern films, paintings, and even textbooks have quietly trained us to expect. Think about how many depictions of ancient or medieval Europe you have seen over the years, in museums, in movies, in school illustrations, all of them defaulting to the same pale complexion, regardless of exactly which century or region was being portrayed. Most of those images were never built from evidence at all. They were built from assumption, borrowed quietly from whatever the artist already knew. Modern Europeans tended to look like projected backward across thousands of years without a second thought. This is exactly the piece that finally makes sense of someone we already spent real time with earlier in this journey. Remember the man discovered in that English cave, dark-skinned, strikingly blue-eyed, dated to roughly 10,000 years ago, right at the very edge of when farming was only just beginning to reach the far western edges of Europe. He was never some strange, isolated exception to the rule. He was, according to this far larger dataset, an entirely typical resident of his moment in European history. The surprise was never really about him. The surprise was about how long that same reality persisted, for how many generations after him across how much of the continent. It means the reconstruction we spent so long examining in the first cave was not an outlier. The wider data quietly contradicts. It was in a strange way a preview, one early data point in a pattern. Researchers would only fully confirm decades later, across hundreds of additional skeletons scattered from Siberia to Scandinavia. So why the delay? If the gene for lighter skin had already arrived with the farmers, and if the pressure favouring it, less usable sunlight, weaker seasonal daylight was already firmly in place across most of Europe, what actually slowed things down for thousands of years afterward? Part of the answer involves something we have not yet properly discussed, and it deserves its own moment here. When farming arrived, it did not simply bring new crops. It quietly reshaped the entire diet of everyone who adopted it. Hunter-gatherer communities, the kind Cheddar Man himself belonged to, relied heavily on fish, wild game, and other naturally vitamin D-rich foods, diets that could partially compensate for weak sunlight in a way farming communities increasingly could not. As populations shifted toward grain-based agriculture, that dietary cushion largely disappeared. Bread does not contain meaningful vitamin D. Neither do most cultivated grains, nor the porridge and later the beer made from them. In a strange, almost cruel twist, the very transition that eventually helped spread pale skin genetics may also have simultaneously stripped away one of the older dietary defenses that had been quietly protecting people against the consequences of not having it yet. A community moving from the coastline into a farming settlement inland was not simply choosing a new lifestyle. It was, without realizing it, giving up one form of protection at almost the exact moment it needed a replacement most. There is a second layer to this delay too, one that has less to do with biology and more to do with simple population mixing. Farmers migrating into Europe did not simply replace the hunter-gatherers already living there. They intermarried with them, sometimes extensively blending genetic lineages together over dozens of generations in ways that varied enormously from region to region. A gene arriving at high frequency in one small group of newcomers does not automatically dominate an entire population overnight. It has to spread through intermarriage generation by generation, while still competing against whatever local genetic patterns and whatever local exposure to sunlight already existed on the ground. In some pockets of Europe, that process moved relatively quickly. In others, it dragged on for thousands of years longer, shaped by how much contact and how much interbreeding actually occurred between the two populations in any given valley or coastline. The regional picture, in fact, turns out to be stranger and more uneven than a simple north to south gradient would suggest. Some of the earliest evidence for lighter traits anywhere in ancient Europe comes not from the sun-starved farming heartlands you might expect, but from far northern hunter-gatherer communities in Scandinavia, populations who never farmed at all during this period, yet who carried certain light pigmentation variants earlier than many of the farming populations to their south. Geography alone, in other words, never fully predicted the outcome. A cold, dark climate did not automatically guarantee an early transition to pale skin, and a warmer, sunnier one didn't automatically guarantee the opposite. Whatever combination of local diet, local genetic drift, and sheer chance happened to be at play in any one valley or coastline mattered every bit as much as the broad climate pattern layered over the entire continent. Here is a small twist worth sitting with because it complicates the picture in an interesting direction, rather than simplifying it. Light eye colour, unlike light skin, actually reached an early peak during the Mesolithic period, before farming ever arrived at all, then noticeably declined once Neolithic populations began mixing in, before slowly climbing back upward again over the following millennia. Skin and eyes, in other words, were never moving on the same timeline, responding to the same pressures at the same pace. Two different traits controlled by different overlapping sets of genes, each with its own separate tangled history, occasionally rising and falling, almost independently of one another, even while sharing the same bodies, the same populations, the same continent. It is a useful reminder that a person's overall appearance is never really one single story, unfolding on one single timeline. It is several separate stories running in parallel, each with its own pace, its own pressures, its own occasional detours, only ever appearing to us today as one unified, coherent whole. Not every researcher agrees on precisely how much weight to give each explanation for the slow pace of this overall shift. Some emphasize the dietary transition as the dominant factor, arguing that farming communities faced a truly sharper, more urgent form of vitamin D pressure than the hunter-gatherers who came before them, which should have accelerated the spread of light skin rather than delayed it, and that the true story is more about uneven regional mixing than about weak selective pressure. Others lean harder into the genetics of population mixing itself, suggesting that admixture dynamics simply how thoroughly and how quickly different groups actually interbred in a given region matter just as much as any nutritional or environmental pressure layered on top. A third group of researchers points towards something more local, still small differences in cloud cover, coastline access, and traditional diet from one valley to the next, factors far too fine-grained for any single continent-wide model to fully capture. And a few researchers reasonably enough point out that reconstructing pigmentation from fragments of ancient, often degraded genetic material will always carry a certain amount of honest uncertainty, no matter how sophisticated the statistical method behind it becomes. If you are the type of person who likes evolution to move in one clean, obvious direction page after page, this particular stretch of the story will probably frustrate you a little, and I understand that completely. What actually happened was slower, patchier, and far less tidy than that populations of every shade of skin, living alongside one another sometimes for thousands of years, at a stretch long after the gene that would eventually reshape an entire continent had already quietly arrived. If you are getting drowsy right about now, let it happen. There is no reason to fight it. If you would like to share down in the comments how many years you've called your own current home, and how far that happens to be from wherever your own family originally came from, long before anyone ever wrote any of it down, what the farmers actually carried into Europe in the end was never a finished outcome. It was only a possibility a single genetic option dropped into a vast, slow-moving population that would take thousands of additional years and countless individual choices about who married whom and who settled where to finally unevenly sort itself out. There is something worth carrying with you from this particular stretch of the story beyond the raw dates and percentages. Evolution, at least in this case, was never some tidy machine executing a predetermined plan. It was closer to thousands of small, unremembered, entirely ordinary human decisions: who to marry, where to settle, which valley felt like home, repeated across countless individual lives over an almost unimaginable span of time, that only in hindsight, looking backward from where we stand now, resembles anything like a clean, purposeful trend at all. Europe's story turned out to be one of gradual convergence toward lighter skin. But it was never the only place on Earth quietly solving this exact same problem. On the opposite side of the same enormous continent, an entirely separate population was working out its own version of the very same puzzle, using tools so different from the ones we just spent this whole chapter examining that for a long time nobody even realized the two stories were connected at all. Halfway around the globe from the farmland trails of ancient Europe, a completely different set of researchers working decades later sat down with a puzzle that looked deceptively familiar. East Asian populations spread across a huge stretch of the planet from Japan down through China and beyond plainly carried lighter skin than populations close to the equator, in a pattern that echoed almost exactly what we just spent an entire chapter tracing through Europe. The obvious assumption, at least at first, was that the same underlying genetic story must be playing out twice the same genes, the same mutations, simply following the same well-worn evolutionary path in a second location. It turned out to be one of the more elegant wrong assumptions in the whole field, the kind of mistake that only reveals itself once someone actually bothers to check the fine print, rather than trusting the surface resemblance. A team of geneticists led by researcher Bing Su and working in direct collaboration with colleagues studying populations across Cambodia and southern China set out to actually test that assumption directly rather than simply accepting it. Their approach was clever in its simplicity. Rather than comparing East Asians only against Europeans or Africans, they built a three-way comparison. Dark-skinned African populations on one end, light-skinned Northern Han Chinese individuals on the other, and sitting in the middle of this puzzle, a group of Austroasiatic-speaking communities native to Southeast Asia populations, who shared deep, ancient genetic roots with East Asians broadly yet who had never developed the same lighter skin tone at all. That middle group turned out to be the key that unlocked everything. If Southeast Asian populations, genetically closer cousins to modern East Asians than to Europeans or Africans, still carried noticeably darker skin, then whatever genetic switch eventually lightened Han Chinese populations further north almost certainly happened separately some time after these two related lineages had already diverged from one another. It was not an inherited trait passed down from some shared distant ancestor. It had to be something newer, something specific. Think of it almost like two branches growing from the same trunk, one branch staying near the shape. Their shared ancestor already had the other quietly reshaping itself in response to a completely different set of pressures further down its own particular path. Scanning across the entire genome, comparing these three groups against one another in careful detail, the researchers found something that stood out sharply from the surrounding genetic noise. An unusually deep, unusually striking divergence sitting inside a gene called OCA2, a gene already known from other research to shape eye color in various populations around the world as well. This time, though, OCA2 was doing something different, involved in a change tied specifically to skin, rather than eyes, at a completely different location within that same stretch of genetic code. Here is where the story truly splits away from everything we uncovered in Europe. The specific mutation involved here swaps one amino acid for another at a precise point along the OCA2 protein, a change researchers refer to by its exact location position, 615, where a building block called histidine gets replaced by a different one called arginine. This particular substitution turns out to be common across huge stretches of East Asia, and at the same time essentially absent from both African and European populations. It is not a milder version of the European story. It is not even a distant cousin of it. It is an entirely separate genetic event arriving at a strikingly similar visible outcome through a completely different biological door. It helps to understand briefly what OCA2 actually does inside a cell, because the contrast with the European mechanism we spent so long examining earlier turns out to be truly interesting rather than simply technical. Where that earlier gene managed the flow of charged particles across the melanosome's outer membrane, OCA2 works more like an internal pH regulator, helping keep the inside of that same tiny structure at the correct level of acidity for melanin production to proceed efficiently. Push that internal environment even slightly off balance, and the whole pigment-making process slows down the same way a chemical reaction in a classroom experiment sputters and stalls the moment the mixture drifts outside its ideal range. Two entirely different mechanical systems, in other words a membrane gatekeeper on one continent, an internal pH regulator on the other, both nudging the exact same underlying chemistry in the exact same general direction. To confirm the mutation actually did what the genetic data suggested, the research team turned to laboratory experiments strikingly similar in spirit to the zebrafish work we spent real time with earlier tonight, though using this particular gene rather than the one behind the European story. Introducing the altered version of OCA2 into both zebrafish and mice, researchers watched melanin production measurably drop in both animals, exactly the functional confirmation needed to move this finding from an interesting statistical correlation to a genuine demonstrated cause. It is worth pausing on how satisfying that kind of confirmation actually is to a working scientist. A correlation in a spreadsheet can always be coincidence, one pattern among thousands that happen to line up by chance. Watching an animal's own pigment cells visibly change color in real time after the exact same mutation is deliberately introduced is a different order of proof entirely. Sit with the shape of that discovery for a moment, because it is worth appreciating properly. Two populations separated by an entire continent and tens of thousands of years of independent history arrived at visibly similar lighter skin through two entirely unrelated genetic solutions, neither one borrowed from the other. Nature faced with roughly the same underlying problem, weak seasonal sunlight, the same trade-off between vitamin D and folate. We spent so long unpacking earlier, did not simply reuse one successful blueprint twice. It solved the exact same puzzle from scratch in two different rooms, using two completely different sets of tools, and somehow still landed on remarkably similar answers. Biologists actually have a name for this pattern, when unrelated groups independently stumble onto similar solutions to similar problems, convergent evolution, and it shows up again and again across nature wings, evolving separately in insects, birds, and bats, or eyes evolving independently dozens of separate times across the entire animal kingdom, each version built from slightly different raw material, each one arriving more or less at the same basic useful idea. Skin color, it turns out, that belongs on that same list, sitting right alongside wings and eyes, as one more example of evolution reaching the same conclusion by more than one road. Have you ever solved a difficult problem only to discover later that someone else in a completely different place, working with completely different resources, arrived at almost the exact same solution, entirely independently? Biology, it turns out, does this constantly, and this particular case is one of its more striking examples. There is something almost reassuring about it if you think about it for long enough. It suggests the pressure was real, urgent, and universal enough that more than one population working with completely different genetic starting material found its way to roughly the same answer, simply because the problem itself demanded it. There is more texture to this story than a single gene can capture on its own, and it is worth walking through it honestly, rather than tidying it up into something simpler than it actually is. A second location within OCA2, a different variant entirely, shows an oddly specific geographic pattern of its own, reaching its highest frequency not broadly across East Asia, but concentrated instead among populations speaking Altaic languages, communities scattered across Mongolia, and the northernmost reaches of East Asia regions where winter sunlight is scarce, even by the standards of the rest of the continent. Meanwhile, the original histidine to arginine variant we already discussed shows its own distinct pattern, reaching nearly 80% frequency among modern Japanese populations, and settling somewhere between 50 and 65% across several different Chinese ethnic groups, including communities as varied as the Dai, the Miao, and the Tujia, each with their own separate histories, their own separate migrations layered underneath this one shared genetic thread. East Asia, in other words, was never one single uniform genetic story either, any more than Europe turned out to be in the chapter before this one. It was several overlapping, only partially connected stories, each shaped by its own particular corner of an enormous geographically diverse landmass. That detail alone should already be quietly reshaping how you think about a phrase like light-skinned East Asian, as though it described one single uniform outcome rather than a patchwork of related but truly distinct genetic histories layered on top of each other. It is a small but important habit worth carrying forward for the rest of this journey. Two people standing side by side with what looks to the naked eye like nearly identical skin tone may be carrying almost entirely different genetic explanations underneath that shared appearance, one person's ancestors having solved this problem through a gatekeeper protein, another's through a pH regulator, another's through some combination neither of us has even discussed yet tonight. Skin color, in other words, is less like a single word with one fixed meaning, and more like a sound that several unrelated languages happen to pronounce almost the same way, for reasons that have nothing to do with one another at all. Not every question here has a tidy answer either, and the researchers involved have been careful to say so plainly. Scientists still debate exactly how strong the selective pressure toward lighter skin actually was across different parts of East Asia, and whether vitamin D synthesis alone fully explains why this particular corner of the world solved the problem the way it did, or whether additional pressures, cultural practices around clothing and shelter, Localized diet, even patterns of who tended to marry whom within a given region, shaped the final outcome as much as raw sunlight ever did. A handful of researchers have gone further still, proposing that something else entirely unrelated to sunlight or nutrition at all may have nudged certain populations toward favoring lighter skin over many generations, an idea we will spend real time weighing honestly a little later in this journey, once we've gathered enough evidence to judge it fairly. Other researchers point out that East Asia's own geography is unusually varied, stretching from subtropical coastlines to frigid northern plains, which likely means no single explanation was ever going to cleanly account for the entire region at once, any more than one explanation could ever fully account for all of Europe either. And more than one scientist working in this specific field has been candid about the fact that East Asian pigmentation genetics remains even today considerably less thoroughly mapped than the European story we spent so long following earlier, simply because so much more research funding and attention has historically flowed toward European populations rather than being distributed evenly across the whole human family, an imbalance the field itself is only slowly beginning to correct. If you have been quietly assuming this entire journey that light skin must be one single trait with one single explanation, wearing different disguises depending on which population you happen to be looking at, this particular chapter is probably the clearest evidence yet that the truth was never that simple. It was never one invention copied and pasted around the globe. It was closer to several separate teams working in isolation, occasionally arriving at strikingly similar answers, and just as often arriving at answers that only partially overlap. If your body is starting to feel heavy and warm right about now, let it sink further into whatever is holding you. There is nowhere else you're supposed to be tonight. If you would like to tell me down in the comments what part of the world you're listening from right now, and what the sky looked like there today, cloudy, clear, somewhere in between. We have now walked through two entirely different populations on two entirely different continents, each independently solving the very same evolutionary riddle in its own way. There is a certain quiet comfort in that if you let yourself sit with it for a moment. Two groups of people who would not meet each other for tens of thousands of years, who never shared a single conversation, a single trade route, a single idea, still ended up facing the same basic problem. The sky handed every population that wandered far enough from the equator, and both in their own separate ways found a way through it. Nobody copied anybody. Nobody needed to. But there is a third piece of this puzzle we have mostly left untouched so far tonight, and it happens to be the piece most people assume needs no explanation at all. We have spent this whole journey treating Africa largely as a single starting point, the place everyone's story began before branching outward into all these different directions. That assumption, as it turns out quietly, overlooks one of the more fascinating chapters in this entire story, sitting right there at the very beginning the whole time. Far south of the equator in the dry red-gold expanse of the Kalahari and the northern cape of South Africa communities, whose ancestors have called this land home for longer than almost any human lineage on the planet, still gather, still raise families, still carry forward traditions older than most nations. The Kusan peoples, often described by geneticists as carrying some of the deepest, most ancient branches of the entire human family tree, split away from the rest of our shared ancestry so long ago that their genetic lineage was already distinct, tens of thousands of years before most of the migrations we've spent this whole journey following had even begun. If you wanted to point to a population that represents something near humanity's oldest surviving thread, this would be very near the place you would point. Here's the detail that quietly surprises almost everyone the first time they hear it. Members of the Kusan community are on average noticeably lighter skinned than most other populations across sub-Saharan Africa. Not pale in the way we have spent so many chapters discussing tonight, but lighter measurably and consistently in a way that stands out clearly against the wider genetic backdrop of the continent that raised our entire species. Photographs of Khoisan elders weathered by decades under an unforgiving desert sun still show a warm golden-brown complexion, set noticeably apart from the deep, rich darkness, typical of many populations further north and east across the continent, a visible difference that anthropologists had quietly noted for generations, long before anyone understood the genetics sitting underneath it. For a long time, the easiest explanation available sat right there, ready-made and convenient. European colonization of southern Africa began roughly 300 years ago, and wherever European settlers moved, genetic mixing eventually followed, sometimes willingly, often violently complicating the ancestry of nearly every population they encountered. It would have been simple, almost lazy, to assume that any lighter skin among the Khoisan today was just one more late echo of that colonial history, a genetic footnote borrowed from Europe within the last few centuries. In 2018, a research team led by Meng Lin, then a graduate student at Stony Brook University working alongside anthropologist Brenna Henn, decided to actually test that assumption, rather than simply repeat it. Their work involved years of painstaking sample collection across the Northern Cape and the edges of the Kalahari, building genetic and pigmentation data from hundreds of individuals willing to participate the unglamorous groundwork that rarely makes it into the eventual headline, but without which no genuine discovery is ever possible. What they found did not fit the tidy colonial explanation at all. Searching through the genomes of several hundred individuals from two specific Khoisan communities, the Nama and the speakers known as the Suscha Komani San, the team looked specifically for a genetic variant that should by now feel like an old familiar face. The exact same single-letter mutation inside the gene SLC24A5 that we spent real time examining earlier tonight, the one responsible for such a striking share of the skin color difference across European populations, showed up here too, at frequencies reaching as high as 53% in some of these communities. That number alone should stop you for a second. Frequencies that high simply cannot be explained by 3 centuries of occasional colonial era mixing. The math does not work. Something else, something much older, had to be responsible. Using careful demographic modeling comparing genetic signatures across multiple related populations, Lin and Henn traced the actual origin of this variant, and the answer took the story somewhere nobody had expected. The mutation had not arrived from Europe at all. It had arrived from East Africa, carried south by pastoralist communities, herding sheep and goats roughly 2,000 years ago, a full millennium and a half before the first European ship would ever round the southern tip of the continent. Those East African herders, likely speakers of Cushitic languages with roots stretching back into the Horn of Africa, had themselves picked up the mutation generations earlier, still through their own long history of contact and intermarriage with populations moving out of the Middle East, the same broad genetic current that had already carried this exact mutation into Europe entirely separately. As these herders pushed steadily southward across the continent following pasture land, following water, following the same practical logic that has guided herding cultures for thousands of years, they carried more than livestock with them. They carried, without knowing it, a small genetic gift that would eventually reshape the appearance of an entirely different population, thousands of miles from where either group had originated. Sit with the shape of that journey for a moment, because it really is remarkable when you trace the whole arc of it. A single genetic mutation born once in one person somewhere in the ancient Near East. One branch of it travelled north and west, eventually reaching the farmers we spent real time with earlier, who carried it into the heart of Europe. A completely separate branch of that same mutation travelled south instead through East Africa, riding along with herders and their livestock for well over 1,000 years, before finally arriving among the Khoisan of the far south, an ocean and an entire continent away from where European history usually places this story. Have you ever assumed something about a person's ancestry based purely on how they look, only to discover the actual explanation travelled through a route you never would have guessed? This is exactly that feeling written into the human genome itself at continental scale. Once the mutation actually arrived among the Khoisan, something else remarkable happened. Something that turns this from an interesting migration story into one of the more striking examples of rapid human evolution ever documented. Natural selection did not simply allow the new variant to sit quietly at low frequency. It pushed hard, favoring it aggressively generation after generation, in a process researchers measure using something called a selection coefficient, essentially a number describing how strongly a particular gene variant improves someone's chances of surviving and reproducing compared to the alternative. To put that in perspective, most genetic variants under active selection carry coefficients so small they're difficult to even detect without enormous sample sizes and considerable statistical patience. The value researchers calculated for this specific variant among the Nama and Komanisan ranks among the strongest, fastest signals of ongoing natural selection ever recorded in modern humans anywhere for any trait. In roughly 2,000 years, a blink of an eye by evolutionary standards, this one mutation went from a rare genetic visitor to a defining feature carried by roughly a third to over half of the population. Individuals carrying 2 copies of this variant measure on average nearly 14% lighter in skin tone than the general community average. On its own, this single genetic locus accounts for somewhere around 15% of the total measured variation in baseline skin pigmentation among the Khoisan today. For one gene arriving from thousands of miles away, carried by herders whose names and faces have been lost entirely to history, that is an extraordinary amount of influence to still be exerting on human bodies today. There is a strange, quiet postscript to this discovery worth mentioning too. Modern commercial genetic testing companies, the same kind we mentioned once or twice earlier tonight, occasionally flag this exact variant in African test takers, and without the full context we just walked through together, sometimes suggest it as evidence of recent European ancestry. It almost never is. More often it is this far older, far more interesting African story quietly reasserting itself, misread by an algorithm that has no way of distinguishing a 2,000-year-old herding migration from a much more recent, far more painful colonial one. Why would southern Africa, so much closer to the equator than northern Europe, still favour lighter skin strongly enough to drive a selective sweep? This fast, researchers point to the region's particular geography drier, higher in elevation across much of the Kalahari than the deep humid tropics further north, with intense but seasonally variable sunlight that behaves somewhat differently than the year-round equatorial intensity we discussed several chapters ago. Higher elevation means thinner atmosphere overhead, which in turn means a greater share of ultraviolet light actually reaching the ground on a clear day, even at a latitude that would suggest otherwise. The same basic trade-off between vitamin D and folate we spent so long unpacking earlier likely still applied here, simply tuned to a slightly different set of local conditions than either the European or East Asian versions of this same story. Does that not complicate every simple, tidy assumption you might have carried into tonight about which parts of the world are supposed to be light-skinned and which parts are supposed to be dark latitude alone was never the whole equation? Elevation, local climate, diet, and the specific genetic material a population happened to be carrying when it arrived somewhere all mattered together in combinations too specific and too local for any single global rule to fully predict in advance. Here is the part of this discovery that carries the most weight, at least for me, once you actually sit with it honestly. For generations, popular assumption has quietly treated lighter skin wherever it appears as some kind of implied marker of European contact or influence, an idea baked so deeply into casual conversation that most people never even think to question it. The Khoisan story dismantles that assumption completely, using nothing more than careful genetic detective work. The very same molecular signature that lightens skin across an entire European continent, also entirely independently of any European history whatsoever, Lightened skin across a completely different population on a completely different continent centuries before Europe and southern Africa had any meaningful contact with one another at all. It is worth pausing here to notice how differently this story unfolds compared to the two we just finished tracing. Europe inherited its version of this mutation through migration, then waited thousands of years while it spread slowly and unevenly. East Asia never touched this particular gene at all, solving the same problem through a completely unrelated piece of genetic machinery. The Kusan borrowed the exact same molecular tool Europe used, yet arrived at their own outcome through a route entirely their own, on a timeline dramatically faster than either of the other two stories we have followed tonight. Not every detail of this story has been fully settled even now. Researchers continue debating the exact route and timing of the East African pastoralist migrations that first carried the mutation southward, since the archaeological and genetic evidence for population movements that old and that far removed from written history is inevitably incomplete. Some researchers emphasize the herding lifestyle itself as the key vector, arguing that livestock movement created exactly the kind of sustained contact needed for genes to travel such distances. Others focus more on the astonishing speed of the selective sweep once the mutation actually arrived, treating that as the more scientifically remarkable half of the story, regardless of exactly how the gene got there in the first place. And more than one researcher has been candid that a discovery this recent in a field still actively gathering new ancient genetic data from underrepresented populations may well be revised or refined as more evidence surfaces. If you are getting sleepy right about now, that is exactly where this story wants to leave you, somewhere quiet, somewhere unhurried. Let your breathing settle into whatever rhythm feels natural, and stop trying to hold your eyes open if they do not want to be held open any longer. If you would like to share down in the comments one thing about your own ancestry that once surprised you, something you assumed was true until you actually looked closer. There is a broader lesson sitting underneath this particular chapter, one worth carrying forward as we near the final stretch of tonight's journey. Africa was never the single uniform starting point so many casual assumptions quietly treat it as. It holds more human genetic diversity within its own borders than the rest of the entire world combined, a direct consequence of simply being where our species spent the overwhelming majority of its history before anyone ever left. A person from the Kalahari and a person from the West African coast can carry more genetic difference between them than a person from Norway carries, compared to someone from Japan, a fact that rarely makes its way into the simplified single-colour version of Africa so many outside the continent quietly carry around in their heads. Skin colour across that continent was never one shade frozen at the beginning of the human story, waiting patiently for everyone else to eventually catch up or diverge from it. It was already moving, already adapting, already telling several separate stories of its own long before any of the migrations we've spent this journey following ever crossed a single border. We have now traced this same evolutionary puzzle across three entirely different populations, three entirely different continents, each one arriving at its own version of the answer through its own particular history. But every single population we have discussed so far tonight shares one thing in common. Every one of them belongs to us, to Homo sapiens, one single species, working out one shared problem in several different ways. There is one more group worth meeting before this night is through cousins of ours who vanished from the world tens of thousands of years ago, who faced this exact same sun, this exact same sky, and who may have arrived at some startlingly similar answers using genetic tools that had nothing to do with our own at all. In 2007, in a laboratory shared between researchers at Harvard University and the University of Leipzig, a small team led by Holger Rempler, working closely with Spanish geneticist Carl Lalueza-Fox and Max Planck Institute researcher Michael Hofreiter, opened two ancient bone fragments that had been waiting patiently for tens of thousands of years to finally be asked the right question. One fragment came from a cave called El Sidron in northern Spain, roughly 43,000 years old. The other came from a site called Monte Lessini in Italy, closer to 50,000 years old. Both belong to Neanderthals, our closest extinct relatives, the other branch of humanity that shared this planet, this exact same sky, for hundreds of thousands of years before finally disappearing from it entirely. Picture the two fragments sitting under laboratory light, unremarkable to the eye, brittle enough that a careless touch could destroy in seconds what had survived tens of thousands of winters intact. The team was searching for one specific gene, the same one we spent real time with earlier tonight, buried inside a completely different, much older population's genetic memory. And this time, extracting it required extraordinary care. Ancient genetic material this old survives only in fragments damaged by time, contaminated easily by the very researchers trying to study it, requiring painstaking verification at every single step, just to be certain the results belong to the Neanderthal specimen, and not to someone who had merely touched the bone centuries or decades later. Contamination is not a minor inconvenience in this kind of work. It is the single greatest threat to the entire result, capable of quietly overwriting tens of thousands of years of history with nothing more than a careless breath or an ungloved fingertip. What they eventually confirmed after checking their results against roughly 3,700 modern human genetic samples to rule out contamination entirely was a variant that had never once shown up in any living person tested. A single altered position along the gene where one particular building block had been swapped for another, in a pattern found nowhere in the many thousands of modern humans researchers had already studied. Here is where the story gets truly interesting, and where it connects directly back to something we spent real time examining earlier tonight in a completely different context. This same gene in modern humans is the one responsible for red hair and the palest, most sun-sensitive skin tones found anywhere in our species, the switch that decides whether a person's pigment cells default toward protective dark eumelanin or the far more delicate, far less protective reddish pigment instead. When researchers tested the Neanderthal version of this mutation in the laboratory engineering human cells to carry it, and observing what happened, the results were unmistakable. This variant meaningfully reduced the receptor's activity in exactly the kind of way that produces red hair and pale freckled skin in people alive today. Sit with the shape of that finding for a moment because it deserves real attention. Neanderthals, an entirely separate branch of humanity, one that split away from our own ancestors roughly 500,000 years before either group ever crossed paths again, appear to have independently evolved their own version of red hair and pale skin through their own separate mutation in the exact same gene modern humans would later use to arrive at a strikingly similar appearance. Researchers estimate that perhaps around 1% of the Neanderthal population may have carried this particular trait, a small but real minority, walking around some Ice Age European landscape with fair skin and reddish hair tens of thousands of years before anyone who looked anything like that would exist among our own species. Try to picture it honestly for a moment, a Neanderthal hunting party moving through a snow-dusted forest, somewhere in Ice Age Europe, most of them dark-haired and one or two among them, by pure genetic chance carrying a shock of red hair and pale freckled skin entirely unremarkable to the rest of the group, simply one more ordinary variation among people who had no framework at all for thinking about any of this the way we do tonight. Have you ever imagined an entirely extinct species of human and pictured them all looking more or less identical, faceless, uniform, interchangeable? This single discovery quietly dismantles that image completely. Neanderthals had their own range of appearances, their own individual variation, their own version of the same basic genetic lottery every human population has always carried within it. It is worth remembering too that Neanderthals were never the only other branch of humanity our ancestors crossed paths with. Further east, another cousin lineage entirely known to researchers mainly through a single finger bone and a handful of teeth, found in a Siberian cave left its own separate genetic trace in the people making their homes at high altitude in the Himalayas. Today, a trace tied not to skin color this time, but to breathing thin mountain air without difficulty. Humanity's family tree, it turns out, had far more branches quietly overlapping with our own than most of us ever learned in school. Why would this particular trait have shown up at all in a species that split from our own lineage so long ago? The explanation lines up neatly with almost everything we have spent this entire night exploring. Neanderthals occupied Europe and parts of Western Asia for more than 200,000 years before modern humans ever arrived there at all. That is an enormous stretch of time spent adapting to exactly the same weak seasonal high-latitude sunlight we have spent so many chapters discussing tonight. The same fundamental trade-off between vitamin D and folate, playing out across an entirely different lineage of the human family tree. To put that timeline into perspective, 200,000 years is roughly 20 times longer than the farmers we spent an earlier chapter following had been living in Europe by the time half the continent still carried dark skin. Given that much more time under that much more sustained pressure, it would honestly be more surprising if some Neanderthal populations had not eventually arrived at their own version of paler, more sun-tolerant skin. There is a second layer to this story, one that only became clear years later, and it complicates the picture in a direction I find quietly moving rather than simply interesting. Modern humans and Neanderthals did not remain strangers forever. When our own ancestors finally pushed out of Africa and into territory Neanderthals had already occupied for hundreds of thousands of years, the two populations met and in more than a few cases interbred something. The fossil and genetic evidence makes unmistakably clear, even though we will never know the individual stories behind any single one of those encounters. Nearly every person alive today whose ancestry traces outside Africa carries a small but measurable trace of actual Neanderthal genetic material, typically somewhere between 1 and 4% of their entire genome, a quiet inheritance passed down from encounters that happened tens of thousands of years ago. It is worth pausing on how strange that fact actually is, once you let it sink in properly. Two different species of human beings, similar enough biologically to produce children together, and different enough that one of them no longer exists anywhere on the planet at all. In 2014, geneticists Sriram Sankararaman and David Reich, working with a team at Harvard Medical School, mapped exactly where, in the modern human genome that inherited Neanderthal material, tends to survive most strongly today, using data drawn from more than 1,000 people across several continents. What they found surprised even the researchers themselves. Far more than almost any other category of trait, the Neanderthal genetic material that persisted most successfully into modern humans clusters specifically around genes tied to skin and hair. One particular example, a gene called BNC2, linked to skin pigmentation and freckling traces directly back to Neanderthal ancestry, and today it survives in something near 70% of all Europeans, a piece of an extinct species quietly living on inside the skin of millions of people who have likely never once heard the name Neanderthal in connection with their own appearance. Here is the detail that keeps this from becoming too tidy a story, and it is worth being honest about it rather than smoothing it over. The specific red hair mutation discovered in those two ancient specimens, the one we started this chapter with, does not appear to be the same variant carried by modern redheads today. It seems, as far as researchers can currently tell, to have simply died out along with the rest of the Neanderthal lineage, never successfully passed down through the interbreeding that did preserve genes like BNC2. Two separate branches of humanity. In other words, each independently discovered a path toward paler, more sun-tolerant skin, in a strange, almost poetic echo of the exact same pattern we watched unfold between Europe and East Asia earlier tonight, except this time the two populations involved were not simply distant relatives, but two genuinely different species of human being. Only one branch of that particular discovery survived to reach you tonight. The other quietly vanished along with almost everything else about the people who carried it. That is worth sitting with for a second because it complicates any simple, tidy narrative about inheritance. Some Neanderthal traits made the crossing into our species and thrived. Others, including the very trait we just spent so long discussing, seem to have been lost entirely, even while the broader category of skin and hair genetics kept right on flowing between the two populations. Evolution, even at the level of extinct species meeting living ones, was never a clean all-or-nothing handoff. It was closer to a river splitting into channels, some of which kept flowing, others of which simply dried up and disappeared, for reasons we may never fully reconstruct from what little evidence survives. Researchers have their own working theories about why some Neanderthal genes thrived in our genome, while others quietly vanished, some tied to basic genetic compatibility between two closely related but not identical species, others tied to simple chance. A variant found in only a small founding group of hybrid descendants, easily lost across a few unlucky generations, regardless of whether it happened to be useful. Not every question here has a settled answer, and researchers are careful to say so. Some scientists caution that a sample size of only 2 ancient specimens is a remarkably thin foundation for estimating how common red hair or pale skin actually was across the entire Neanderthal population, spread as they were across a huge and varied stretch of Europe and Western Asia over hundreds of thousands of years. A population that large spread across that much territory almost certainly held far more pigmentation variation than 2 isolated bone fragments could ever fully capture the genetic equivalent of trying to describe an entire ocean from a single cup drawn out of it. Others argue that even a small sample confirmed through careful laboratory testing rather than genetic guesswork alone still represents meaningful evidence, simply evidence that deserves to be treated with appropriate humility rather than dismissed outright. And more than one researcher has pointed out that we are, in a very real sense, reconstructing the appearance of an entire vanished branch of humanity from fragments smaller than a coin, a task that will always carry some irreducible uncertainty, no matter how sophisticated our tools eventually become. If you're drifting further into sleep right about now, let yourself go there completely. There is nothing left to hold on to tonight except the sound of this, and wherever you happen to be resting, that is exactly where you're meant to be. If you would like to tell me down in the comments whether you have ever taken one of those consumer genetic tests that reports a Neanderthal ancestry percentage and what number came back for you. Here is what stays with me most long after learning all of this. Somewhere in the DNA of a majority of people watching this tonight, if your ancestry traces outside Africa, sits a small, quiet inheritance from a species that no longer exists anywhere on Earth. Every freckle, every particular shade of skin shaped even partly by that one gene, carries forward something that would otherwise have vanished completely, tens of thousands of years ago in the cold hills of an Ice Age Europe neither you nor I will ever get to see. There is something almost tender about that if you allow yourself to feel it. A species that no longer draws breath anywhere on this planet is in a very real and measurable sense still here, still quietly visible in the freckles across someone's shoulders, in the particular way sunlight catches a certain shade of skin, an inheritance carried forward by people who will go their entire lives never knowing exactly whose gift it was. We have now spent this entire journey tracing how skin color evolved again and again across separate continents, separate populations, and now remarkably separate species entirely. Each one solving the same fundamental problem with whatever genetic tools happen to be available to them. But not every explanation you will encounter about this subject comes from careful, peer-reviewed science, like everything we have covered so far tonight. There is a whole other layer to this story, theories that sit somewhere between legitimate scientific debate and much shakier ground, and it deserves an honest look before this night is through. Everything we have walked through so far tonight, the folate, the vitamin D, the genes, the migrations, the extinct cousins who solved this same riddle in their own quiet way, sits on truly solid scientific ground, tested, published, argued over by careful people doing careful work. What comes next is a little different, and I think it is worth being honest about that difference before we go any further. These next few ideas reside in a messier part of the field taken seriously enough to appear in real academic journals, yet nowhere near the kind of settled consensus everything else tonight has earned. A Canadian anthropologist named Peter Frost noticed something that the vitamin D and folate story, for all its explanatory power, never quite fully accounts for. It is not simply that European populations became lighter-skinned. It is that European hair and eye colour exploded into an almost bewildering range of variety. Blonde, flaxen, auburn, deep brown, alongside eyes that can land anywhere across blue-green grey or hazel, a palette found nowhere else on the planet at anything near this density. Walk through almost any other part of the world, and hair and eyes tend to cluster tightly around dark brown to black. Northern and Eastern Europe stands out as a striking exception, a region where an ordinary family gathering might include half a dozen truly different combinations of hair and eye colour among near-blood relatives. Natural selection driven purely by sunlight should in theory push a population toward one single most efficient answer, not toward an entire rainbow of competing options sitting side by side within the same small region. So Frost went looking for a different kind of explanation and landed on something considerably more provocative than sunlight and vitamins. His proposal centers on the brutal mathematics of survival during the deepest, coldest stretch of the last ice age across the open steppe and tundra of what is now northern and eastern Europe. Hunting large, dangerous game in that kind of unforgiving landscape was overwhelmingly a male activity, and a lethal one, the kind of work that killed young men in their prime with grim regularity long before modern medicine or reliable shelter existed to soften the odds. If men were dying at meaningfully higher rates than women during this period generation after generation, the surviving population would have skewed further and further toward more women than available men. Frost's argument is that this imbalance flipped the usual direction of a very old evolutionary dynamic. Instead of men competing to attract choosy women, as tends to happen across most human societies, a shortage of surviving men may have left women competing harder to stand out to the smaller pool of available partners, favouring whatever visibly rare eye-catching traits happen to us appear purely because novelty itself became attractive in a population desperately short on choice. Have you ever noticed how a single unusual detail, a rare hair colour, an uncommon eye shade can catch someone's attention, purely because it stands out from everyone around it, with no deeper meaning attached at all? Frost's hypothesis leans directly into that instinct, arguing it operated at the scale of an entire population across thousands of years, quietly reshaping the visible palette of an entire region. It is a strangely intimate idea when you actually sit with it. The notion that something as sweeping as an entire continent's colour palette might trace back not to sunlight or nutrition at all, but to something closer to attraction. Repeated across countless individual choices nobody involved ever thought of as scientific in the slightest. There is something almost humbling about picturing it that way, an entire visible feature of a continent's people, shaped not by some grand external force pressing down from the sky, but by thousands of quiet, unremarkable moments of one person simply noticing another. It is a truly interesting idea, and Frost has argued it with real rigour across more than one academic publication, tracing everything from the specific genes involved in hair and eye colour to the geographic boundaries of where this diversity peaks most sharply. But it has not gone unchallenged, and the challenges are worth taking seriously rather than glossing over. A study published in the American Journal of Physical Anthropology specifically tested one of his core predictions that women in higher, colder latitudes should show noticeably lighter skin relative to men from the same population, a pattern his model requires, if sexual selection really did act more strongly on female appearance than male appearance. The results researchers found complicated that prediction considerably, rather than confirming it cleanly. Other critics point out that the entire model leans heavily on an assumption of widespread polygyny and a specific, hard-to-verify sex ratio imbalance among Ice Age hunter-gatherers, evidence that is inherently difficult to reconstruct with any real confidence from skeletal remains this old and this fragmentary. Skeletons, after all, can tell a great deal about how someone lived and died, but very little about how many potential partners were actually available to them at any given moment in their community. I want to be honest with you about where this leaves us. Frost's sexual selection hypothesis remains a minority position within the field, provocative enough to keep generating debate but nowhere near displacing the vitamin D and folate framework we spent so much of tonight building together. Most researchers studying this today treat it as an interesting supplementary question. Why did diversity specifically explode in this one region, rather than a genuine rival explanation for why skin lightened at all in the first place? It occupies a strange, uncertain middle ground, too carefully argued to dismiss outright, too thinly supported, to comfortably accept exactly the kind of open question honest science is willing to sit inside without rushing toward a tidy answer just to make the discomfort go away. There is a second contested idea worth sitting with tonight, one that circles back to something we already spent real time discussing and quietly complicates it further. Roughly 1/3 of adults worldwide can comfortably digest milk into adulthood, a trait called lactase persistence, and it is overwhelmingly concentrated in populations with deep roots in Northern Europe. For years, the leading explanation, sometimes called the calcium assimilation hypothesis, proposed a tidy, satisfying connection to everything we already covered earlier tonight. If sunlight in Northern Europe was too weak to reliably produce enough vitamin D through skin alone, and if lighter skin itself was only a partial solution, then milk rich in both calcium and a modest amount of vitamin D could have offered populations there a critical dietary backup, and the ability to digest it into adulthood would have carried an enormous survival advantage, particularly for children still growing bones and for mothers who had already given so much of their own calcium reserves to a developing infant. It is an elegant idea. Unfortunately, elegant and correct are not always the same thing, a lesson this entire field seems to relearn every few years, usually right around the moment someone finally gets around to checking. In 2014, a research team led by geneticist Yvonne Sverrisdottir set out to actually test that assumption using ancient DNA, rather than simply accepting how tidy the story sounded. They examined skeletal remains from early farmers in Iberia in modern-day Spain, a region blessed with considerably more reliable sunlight than Northern Europe ever had. The logic of the test was almost beautifully simple, the kind of clean experimental design researchers dream about. If the calcium assimilation hypothesis were correct, farmers living somewhere this sunny should have faced little pressure to evolve lactase persistence at all, since their skin could presumably produce plenty of vitamin D on its own without any help from dairy. Running careful simulations against the ancient genetic data they recovered, comparing how quickly the relevant mutation would need to have spread to match what they actually found in the bones, the team found something that did not fit that expectation in the slightest. The genetic signature for lactase persistence appeared to be spreading through sun-drenched Iberian populations at a pace that still required real active natural selection. The same kind of pressure you would expect somewhere far less sunny. Sit with that contradiction for a moment because it truly unsettles the tidy version of this story. If milk drinking were purely about compensating for weak sunlight, sunny Iberia should have been the one place in Europe where this particular trait had little reason to spread at all. Instead, it spread there anyway at a pace suggesting something else entirely was driving it, something researchers are still actively trying to identify. Some have proposed that milk offered protection during periods of famine or crop failure, a reliable calorie source when harvests failed. Others have suggested it may have carried some protective advantage against disease, or even functioned as a kind of practical high-status behavior that spread through cultural imitation as much as biological necessity. Does that not complicate the whole picture in an interesting way? Two separate traits, skin color and the ability to digest milk, both concentrated heavily in the exact same region of the world, both once explained by the exact same tidy story about weak northern sunlight, and yet when researchers actually went looking for direct evidence, the milk story turned out to be far messier than anyone originally assumed. It raises an honest, uncomfortable question worth sitting with. If the calcium explanation does not fully hold up for lactase persistence, how confident should we really be that we have the complete picture for skin color, either rather than simply the most convincing story available so far? I want to be careful here because there is an important difference worth naming clearly. The vitamin D and folate framework behind skin color has survived decades of exactly this kind of testing across ancient genomes, laboratory experiments, and modern population data, and it keeps holding up reasonably well even as researchers keep refining the details. The calcium assimilation hypothesis for milk drinking, by contrast, is the piece that recently failed a direct test, not skin color itself. What the milk story really teaches us is something more general and more useful than a single specific correction. Even the most intuitive, most satisfying explanation in this entire field deserves to be tested rather than simply trusted, no matter how neatly it seems to tie everything else together. I do not think that question should worry you the way it might sound like it should. If anything, I find it reassuring. Science that never revises itself, never argues internally, never tests its own most convenient explanations against inconvenient evidence is not actually science at all. It is just a story that happens to sound finished. The willingness to say, honestly, we thought we understood this, and the data just told us otherwise is not a weakness in how this field operates. It is the exact mechanism that eventually turns a decent guess into something closer to the truth, one uncomfortable correction at a time. There is one more thing worth naming plainly before we move past this particular stretch of the journey. Contested does not mean worthless, and unresolved does not mean anything goes. Frost's hypothesis and the calcium assimilation debate both exist inside a rigorous evidence-based conversation, argued over in peer-reviewed journals tested against real data, revised when that data pushes back. That is a very different category from the kind of confident-sounding nonsense that occasionally circulates about why human populations look the way they do, dressed up to sound scientific while carrying none of the actual discipline science requires. Knowing the difference between an honest, open question and a bad faith claim dressed up to look like one turns out to matter quite a bit, especially given where this story's about to head next. If you're somewhere between awake and asleep right now, let these last few uncertain edges be the thing you drift off holding on to, rather than something that needs resolving before you can rest. Let your body sink a little heavier into the mattress, and stop trying to follow every thread all the way to its end tonight. If you would like to tell me down in the comments, which theory tonight surprised you the most, the tidy ones or the messy ones? Every single explanation we have walked through tonight, the well-established ones and the contested ones alike, shares one thing in common that is worth naming plainly before we move any further. All of it comes from careful people, testing careful ideas willing to be proven wrong by better evidence when it eventually arrives. Nobody in this entire story, from Brander and Eaton in their quiet laboratory, to Ching staring at a strangely pale fish, to Sverrisdottir combing through ancient Iberian bones, ever demanded that you simply trust them. Every one of them showed their work, published their methods, and left the door open for someone else to come along and prove them wrong. That has not always been true of how skin color has been discussed throughout human history. There is a far darker chapter still waiting for us tonight, one where this exact same biological trait was picked up by people with no interest in evidence at all and turned into something it was never built to be. In the 1830s, in a quiet study in Philadelphia, a physician named Samuel Morton began collecting human skulls. He was by most contemporary accounts a meticulous, well-respected member of the city's scientific establishment, eventually rising to head its Academy of Natural Sciences. By the time he finished building his collection, he had assembled hundreds of skulls gathered from around the world through a network of correspondents, soldiers and traders, each one carefully measured, weighed, and catalogued with the kind of obsessive precision that on the surface looked exactly like careful science. His method was almost disarmingly simple. He would pack a skull with mustard seed or later iron shot, pour the contents into a measuring glass and note the volume as a stand-in for brain size. In 1839, he published his findings in a book called Crania Americana and used those numbers to rank entire populations of human beings into a tidy hierarchy, with people of European descent placed confidently at the top and every other population arranged carefully beneath them. It was treated at the time as serious objective science, the kind respectable institutions cited without hesitation. It was in truth nothing of the sort. For more than a century, Morton's work quietly shaped how people thought about human difference, cited approvingly by those looking for a scientific justification for exactly the social order they already preferred. Textbooks referenced his numbers as settled fact. Political speeches leaned on his authority without ever questioning the premise underneath it. In 1981, the biologist and writer Stephen Jay Gould revisited Morton's data and argued in an influential book that Morton had almost certainly let his own expectations distort his measurements. Packing certain skulls a little less carefully than others, thumbs pressing where they should not have pressed until the numbers quietly lined up with what he already believed. It was for its time a powerful and important correction, and it reshaped how an entire generation understood the dangers hiding inside seemingly neutral data. Here is where this story takes a turn I find worth sitting with, honestly, because it does not resolve quite as cleanly as you might expect. In 2011, a team of anthropologists went back and actually remeasured Morton's original skulls themselves, still preserved in a museum collection in Philadelphia, painstakingly working through hundreds of specimens with modern instruments, and none of the assumptions either Morton or Gould had carried into the room with them. Their conclusion surprised a great many people. Morton's original measurements, it turned out, were largely accurate. He did not appear to have physically manipulated his samples the way later critics assumed, and the pattern of any small errors that did turn up showed no meaningful bias favouring one population over another. Does that mean Morton's science holds up after all? Not remotely, and this is the part worth pausing on because it cuts closer to the actual problem than a simple story about fudge numbers ever could. Morton's raw measurements being roughly correct changes almost nothing about the conclusions he built on top of them. Ranking entire populations of human beings into a hierarchy of worth based on the size of a container their brain happened to fit inside was never a legitimate scientific inference in the first place, accurate measurements or not. The flaw was never really in his measuring glass. It was in the question he decided to ask with it, and the answer he had already decided to find before a single skull was ever packed. There is a quieter, less famous figure from that same era worth knowing about, if only for the contrast he offers. A German anatomist named Friedrich Tiedemann, working with strikingly similar data on brain size across different populations around the same period as Morton, gathering comparable measurements through his own careful independent research, reached an entirely different conclusion. Tiedemann used his findings to argue explicitly for human equality and for the abolition of slavery, publishing his own work with the specific intent of undermining exactly the kind of hierarchy Morton was busy constructing an ocean away. Same broad category of evidence, same era. Two trained scientists working independently, arriving at nearly identical raw numbers and sitting on opposite sides of one of the moral questions of their century. Have you ever noticed how the exact same set of facts can be twisted to support whatever someone already wanted to believe before they even started looking? That is not really a story about measuring skulls at all. It is a story about where bias actually lives, not usually in the raw numbers themselves, but in the questions people choose to ask of them and the conclusions they were already reaching for long before the data arrived. Two men, both trained scientists, both working with roughly the same category of evidence, arrived at opposite conclusions almost entirely because of what they had already decided somewhere quieter, and earlier they wanted that evidence to prove. Morton's specific brand of skull ranking eventually fell out of fashion, but the broader cause he represented did not disappear quietly. Through the rest of the 19th century and well into the 20th, similar reasoning was used to justify colonial rule, forced segregation, restrictive immigration policy, and worse, dressed up in the borrowed authority of laboratories and measuring instruments, treated as settled fact by people who had every reason to want it settled in exactly that direction. What made this particular kind of pseudoscience so durable and so dangerous was never really its accuracy. It was the borrowed credibility, the white coats and Latin terminology and carefully ruled measurement table, all of it dressed up to look exactly like the kind of careful, honest science we have spent this entire night actually practicing together. Skin color, the very trait we have spent this entire night carefully tracing back to folate to vitamin D, to a handful of genes scattered unevenly across a shifting migrating species, became for a very long stretch of history treated as though it were a message written in permanent ink about a person's fundamental worth. Here is where everything we built together tonight actually earns its keep. Because we now know with a level of confidence Morton could never have dreamed of exactly how shallow and how recent this particular trait really is. We know it is controlled by a small handful of genes, not some sweeping marker of deep ancestral difference. We know those genes evolved independently more than once on separate continents, using entirely different biological tools to arrive at similar results, a lesson we spent real time earning ourselves, watching Europe and East Asia solve the exact same puzzle through completely unrelated genetic doors. We know the exact same molecular solution reached Europe and Southern Africa through two completely unrelated routes, thousands of years apart, one carried by farmers, the other by herders, following an entirely separate path across an entirely separate continent. We know an extinct cousin species arrived at a strikingly similar answer entirely on its own, using a mutation modern humans never inherited at all. We know Africa alone holds more genetic diversity within its own borders than the rest of the planet, combined making any single skin tone a hopelessly poor proxy for the deep, complicated ancestry hiding underneath it. There is a phrase some researchers in this field have taken to using almost as a quiet rebuttal to men like Morton, describing human skin tones not as a ladder to be climbed, but as a sepia rainbow, an unbroken gradient stretching from the deepest browns near the equator to the palest creams near the poles, with no clean lines anywhere along the way, no natural rung where one category stops and another begins. Morton needed sharp, countable categories to build his ranking at all. Nature never supplied him with any. Every boundary he drew was invented, imposed from outside, a ruler laid across something that had never actually been divided into segments to begin with. If Morton had access to even a fraction of what we walk through together tonight, his entire framework would have collapsed under its own weight before he ever packed a single mustard seed into a single skull. The tragedy is not that the tools to disprove him did not exist yet. Vitamin D had not been discovered. The structure of a gene had not been imagined. The tools simply were not there. the tragedy is closer to something quieter and more uncomfortable that so many people for so long wanted his conclusion to be true, badly enough that nobody thought to demand better evidence before building an entire social order on top of it. Every single piece of tonight's journey taken together adds up to the same quiet, thorough demolition of the hierarchy Morton spent his career trying to build, not through outrage or argument, but simply through patient accumulated testable fact. Not every consequence of this history lives safely in the past, and I think it would be dishonest to pretend otherwise before we finish up tonight. There is a real, measurable, modern-day thread connecting directly back to something we spent real time with earlier, the very disease that sent children to Kurt Hulczynski's mercury lamps in 1918 Berlin. Vitamin D deficiency, and rickets along with it, is quietly returning today, and it is landing hardest on precisely the populations you would predict once you understand everything we have covered tonight. Studies following African Caribbean adults living in the United Kingdom have found more than a third measurably deficient in vitamin D, with a further large share sitting in an insufficient range just above that, together accounting for the clear majority of that population. In the United States, health researchers have documented that nearly half of African American women measured at the end of winter showed vitamin D levels low enough to raise real medical concern, a figure that echoes almost eerily the very statistics that once alarmed Hulczynski's Berlin a century ago, simply relocated to a different country, a different century, a different population entirely. This is not a story about anyone doing anything wrong. It is the same evolutionary mismatch we have circled all night, simply playing out in a modern setting neither evolution nor history ever quite prepared for. Skin that evolved its protective darkness across generations spent near the equator, now for entirely understandable reasons tied to migration history and modern life, often lives at latitudes and indoor lifestyles that same skin was never tuned to handle without support. Consider how differently the two stories look side by side. Hulczynski's patients suffered because industrial smoke stole sunlight from skin that expected to receive it freely. Today's version of the same problem runs almost in reverse: skin built for abundant equatorial sunlight, now living somewhere that sunlight was always going to be scarce, regardless of any smoke in the air at all. Same disease, same underlying vitamin, two almost opposite routes leading to the same quiet deficiency. The very trade-off between folate protection and vitamin D production that shaped this entire story hundreds of thousands of years ago has not gone anywhere. It is still quietly operating inside real people, right now simply relocated to circumstances biology never had time to catch up with. There is at least a truly hopeful piece attached to this particular version of the problem. Unlike almost everything else we discussed tonight, this one has a straightforward, inexpensive fix already sitting on pharmacy shelves everywhere. A vitamin D supplement or a fortified carton of milk, doing quietly and quickly what would otherwise take evolution many more thousands of years to finish sorting out on its own. If you're drifting towards sleep right now, let this be a gentle thought to rest on rather than a heavy one. Let your breathing slow all the way down, and let whatever tension you're still holding somewhere in your shoulders finally let go completely. If it helps picture something warm and ordinary sunlight through a kitchen window, nothing more complicated than that. If you would like to share down in the comments if tonight changed how you think about something you assumed you already understood. Knowledge, like the kind we spent this whole night gathering, carries a quiet kind of responsibility with it, once you actually have it. Morton had a measuring glass and a set of assumptions he never bothered to question. We have something considerably better tonight: hundreds of thousands of years of patient, honest evidence gathered by people willing to be wrong-tested against skulls and skeletons and ancient blood and living genomes, none of it caring in the slightest what any of us might have preferred it to say. That is worth carrying forward long after tonight is over. The next time you catch yourself, or anyone around you reaching for a simple story about human difference that happens to feel a little too convenient, a little too tidy, a little too eager to confirm something you already believed before you started looking. Real evidence rarely arrives that neatly. It tends to be slower, messier, and considerably more interesting than whatever story would have been easiest to believe. We have one final stop left to make before this journey closes, and it is the quietest one of all. Not a laboratory, not an ancient migration, just you and the skin you happen to be sitting in right now, and everything it has been carrying silently this entire time. Let's walk back through all of it one more time, slowly, the way you might flip through old photographs before finally closing the album for the night. It began in a limestone cave in the west of England, with a man who lived and died 10,000 years before anyone would ever think to ask what colour his skin had been, and a laboratory that finally answered that question in a way nobody expected. Blue eyes and skin dark enough to overturn 100 years of quiet assumption in one afternoon. It reached back further still, past him, past farmers, past everyone, to a species that likely started out pale beneath its own fur long before the sun ever demanded anything different of it. A truth hiding inside a gene called MC1R and a population of ancestors that at one strange moment may have numbered fewer than the crowd at a college football game. It found a vitamin most of us have never once thought about, quietly deciding, for hundreds of thousands of years, who would carry a pregnancy safely to term, and who would not uncovered almost by accident by two doctors testing something that had nothing to do with evolution at all. It found the opposite problem waiting on the other side of that same coin, a different vitamin needing exactly the kind of sunlight the first one needed protection from forcing an entire species into an impossible negotiation with its own skin, a negotiation a Berlin pediatrician stumbled into with nothing more than a mercury lamp and a hunch in the freezing winter after a war. It found a fish tank in central Pennsylvania, holding completely by accident the answer to a question that had puzzled serious scientists for generations. One single letter swapped once, somewhere in deep human history, quietly deciding a third of the visible difference between two continents. It found farmers walking slowly across an entire continent carrying a mutation. Inside them, they could not have known was there, and it found that mutation taking thousands of years longer to finish its work than anyone had assumed. Dark skin quietly persisting in Europe, long after we expected it to have vanished right up through the Iron Age, half a continent still wearing a colour modern assumption had quietly written out of the story. It crossed an ocean and a continent to find an entirely separate population solving the exact same puzzle with completely different genetic tools, a gene called OCA2, instead of the one we had already come to know so well, proof that evolution can knock on more than one door and still arrive at a similar answer. It circled back into Africa itself to find that even the birthplace of our entire species was never one single shade to begin with, that the exact same European solution had quietly travelled home again carried by herders, thousands of years before any European ship ever reached that coastline, arriving faster and stranger than anyone studying it expected. It met cousins who no longer exist anywhere on this planet and found quietly living on in freckles and skin tone today, small pieces of a species that vanished tens of thousands of years ago. It sat honestly with theories that remain unresolved, a Canadian anthropologist's provocative idea about competition and colour, a milk-drinking mutation that refused to behave the way anyone expected it to, refusing to pretend more certainty than the evidence actually allows, and it looked directly at the ugliest use this science was ever put to a man with a measuring glass and a set of conclusions he'd already reached before a single skull was ever weighed, and let the evidence itself, hundreds of thousands of years of it, do the quiet work of taking that ugliness apart piece by patient piece, without needing to raise its voice even once. That is where this story has taken us tonight. And now finally it comes back to you. Whatever shade your skin happens to be, wherever you are lying right now as you listen to this, it is not some ancient, unchanging fact handed down unaltered since the dawn of humanity. It is closer to something alive, something that has been quietly negotiating with sunlight for longer than anyone can properly imagine, adjusting, drifting occasionally, reversing course entirely, generation after generation in response to exactly where your particular ancestors happened to be standing when the sun rose each morning. Somewhere in the story of how you came to look the way you do, there is a version of Cheddar Man's cave, a version of Hulczynski's lamp, a version of that one small mutation in a Pennsylvania fish tank, whether your family has ever heard those names or not. Think for just a moment about how many separate decisions had to line up perfectly across how many thousands of generations for your skin to end up exactly the shade it is tonight. Someone somewhere survived a pregnancy that folate quietly protected. Someone else somewhere else survived a childbirth that a slightly stronger pelvis made possible. Somewhere along the line, an ancestor of yours migrated toward the sun, or away from it following food or family or simple curiosity, with absolutely no idea that the decision would still be legible on their descendants' skin tens of thousands of years later. None of them were thinking about you, and yet every single one of them in some small unknowable way helped write the exact shade you're wearing tonight. There is something almost dizzying about that if you actually let yourself sit with the scale of it. Every single person you've ever loved, every stranger you've ever passed on a street in a hurry, every face in every family photograph going back as far as anyone still remembers, all of them carrying forward the exact same kind of quiet, patient inheritance, written in a language none of us can translate directly, only ever see the finished result of staring back at us from a mirror on an ordinary evening like this one. Here is the thought I most want to leave you with tonight out of everything we have covered. The very trait so many people for so much of history tried to use, to draw lines between human beings to rank them to separate them, turns out once you actually follow the evidence all the way down to tell almost the opposite story. It tells a story of one species walking out of one place, adapting again and again to whatever sky happened to be overhead, using whatever genetic tools happened to be available, arriving over and over at slightly different answers to the exact same fundamental question. Different shades, same underlying story, same sun refracted differently across an entire species finding its way around an entire planet. If you have a mirror nearby tonight, or even just the memory of your own hands in front of you, take a quiet moment to actually look the way you might look at a photograph of somewhere you have never been. What you're looking at is not a category. It is a story written slowly, patiently by sunlight and migration, and a handful of genes, none of which ever asked permission, none of which ever cared what conclusions anyone might someday try to draw from the result. If you have made it this far, you have spent the better part of 3.5 hours with me tonight following folate through a laboratory in the 1970s, and vitamin D through a Berlin children's clinic, and one tiny mutation across 2 entire continents, and 1 extinct cousin species. That is not a small thing, and I do not take it for granted for a second. Whatever else tonight has been, I hope it has felt less like a lecture, and more like sitting beside someone who simply could not wait to tell you what they had just learned. I think about this particular story differently than most of the ones we have shared together over time. So many of the nights we have spent together involve people long gone, distant courts, vanished cities live so far removed from your own that they can feel almost like fiction by the time the lights go down. This one was different. This one was never really about anyone else at all. Every single fact tonight, every laboratory, every ancient migration, every contested theory was quietly, patiently building toward the one thing in this entire story that belongs to you personally, undeniably right now without a single exception. Your own skin, still here, still doing exactly what it has always done, holding an entire unwritten history together one quiet layer at a time, whether you ever think about it again after tonight or not. Before I let you go completely, a few small things, only if they feel right to you tonight. If this kind of story is the kind of company you want at the end of a long day, tapping that like button helps more than you would probably guess, and it cost you nothing at all. It is a small, quiet way of telling me this was worth your evening. And every single tap truly does help more stories like this one find their way to more people who might need exactly this kind of company tonight. Following along means you will be here the next time we do this together, whatever quiet corner of history or biology we end up exploring next. I never know in advance who is going to be listening or where or what kind of day they have just had, but I do know I would rather you not miss it when the next one arrives. There is always another thread worth pulling, another quiet corner of the past nobody has properly explained yet, and I would like nothing more than to have you here for it. If you have not already, I would love to know down in the comments where in the world you are tonight and what time it is exactly where you are tucked in listening to this in the dark. I see every single one, and there is something I truly love about picturing all these different corners of the world, all listening to the same story, at completely different hours of their own night, strangers to each other, sharing the exact same handful of minutes without ever knowing it. And if a night ever comes where you would like to support this a little further, there is a small optional way to do that too, entirely up to you. Never anything you owe, never anything I will ever ask twice. Dim the lights the rest of the way now if you have not already. Let your shoulders drop. Let your breathing slow. Somewhere tonight in a country you may never visit, someone with a completely different shade of skin than yours is falling asleep under the exact same explanation. You just heard folate and vitamin D, and one small mutation quietly writing the story of their own particular shade the same patient way it wrote yours. You will likely never meet them. You share this story with them anyway, whether either of you ever learns the other exists. Somewhere else tonight, someone newly born is already carrying forward a negotiation with sunlight that began long before either of their parents existed, that will likely continue long after everyone listening to this tonight is gone, patient and indifferent and utterly reliable, the way only something this old can afford to be. Whatever colour the sun found your ancestors in, it found them all the same way patiently over hundreds of thousands of years, one generation at a time, not judging, not ranking, simply asking the same quiet biological question it has always asked every population it has ever touched, and letting each one answer in its own way at its own pace, with whatever genetic tools happen to be sitting closest at hand. You carry that whole story in your skin tonight without ever having to think about it. It was there this morning before you knew any of this. It will still be there tomorrow after you have forgotten most of the details, the names, the dates, the exact percentages. That is all right. The story does not need you to remember it perfectly. It only ever needed you to carry it, and you already have this entire time without trying at all. Somewhere behind your closed eyes right now, whatever shade you happen to be, the same quiet biology that carried a folate warning across 100,000 years, that carried a single letter across an entire continent, that carried a small piece of an extinct species into your own freckles without asking permission is still there, still working, still in its own patient, wordless way, taking care of you tonight exactly the way it has every single night before this one, long before either of us ever gave it a name. That's enough for now. Thank you for spending this time with me. Sleep well, and next time we will find another quiet corner of history worth stepping into together.